and we will start off with Peter Tiemann.
Thank you. Fully fit the screen. Anyway, so if you've ever been writing programs with session types in a functional language, you will know that this is like a concurrent lambda calculus. You have communication primitives, and they're usually typed like here. So you have, let's say, the send primitive. It takes some data to send. Then the session type, the type of the channel you're sending on, says, on me, you can send an alpha, and then the communication continues according to sigma, and then the primitive returns the depleted channel of the let's call it continuation type sigma here. And as you can see here, the receive primitive has like the same structure, only that now the prefix of the session type says receive an alpha and then continue as sigma, and then of course from receiving you want to return what you received and also the remaining continuation channel. Now this gives rise to a particular, oh, that's interesting. This gives rise to a particular style of program that we like to call resource passing style. Suppose we have a longer session type with two communication actions, sending an integer, receiving a bool, and now we only want to perform a prefix of that calculation. All right, now you do that. After sending the first message, now you are left with, well, receive a bool and close the channel. But notice here, in the type, you have this kind of annoying repetition of this continuation. Well, people have invented polymorphism, maybe not for this, but now you can make this function more flexible by abstracting over the continuation. Yeah, so I say, for all sigma, I just want to send an integer, and then any kind of continuation protocol is okay with this function. Now consider what happens if you want to write some primitive that takes two channels and wants to do two prefixes of the protocols. So this would look like this. So on the first channel, I just want to send an integer and then whatever. On the second channel, I want to send a bool and then do whatever. Now I've got to worry about two continuation channels. And since I'm in this resource passing style, I need to return two of those continuations. And you can imagine if you have 3 and 4, then this gets a bit of a mess. So you essentially have to return all these continuations in a data structure. You can, in this example, I don't really return a result from the calculation, so you would have to pair that as well. Of course, you could say, hey, I can encapsulate that in a monad. This works nicely, but it works only nicely for a single channel. And there's work like, for example, Pucella and Toff, where they did some embeddings in Haskell, and it gets pretty crazy if you look that up for multiple channels. Now, what can we do? So what we are suggesting is that we are introducing a split primitive for session types, which is very similar to what you would do in a borrowing style. And the idea is, if you have a channel type like this, send two integers and then close, then with using a notion of borrowing, which we implement here as a split primitive, you can split it into a borrowed prefix that says, hey, send an integer and then return. And then this gets composed with the remainder, the continuation channel as we had it before. Now, so essentially the split primitive looks like this. If I have a function, if I have a channel type that is composed of a borrowed prefix, that's something ending with return, and then a continuation, then split can split it into the borrowed prefix and this continuation type. And this is not just any pair here, but this is a left to right ordered pair, which prescribes that you have to consume first the borrowed prefix and then the continuation, because otherwise you would be breaking the protocol. And we'll come back to that in a few minutes if we have them. So what are we going to do instead? So we are proposing to replace this resource passing API by a borrowing style API. Yeah, so now the sending takes, instead says, oh, I want to have a single shot channel where I can just send an alpha and then return. So we are only dealing with borrows that just do a single communication. Similar for receive, we're saying, hey, the channel should allow first to receive an alpha and then return. Yeah? So whatever the rest is, that's dealt with by the splitting. And now the types get less messy, I would say, less involved than here. And also the code, well, you can argue about that. In my examples, I'm using sending. Trust me, if I would use receives, then the code here would be much bigger. So here you can already see this typical order reversal that you have when composing functions. So here I have to first I'm sending the last. So in the code, it looks like I'm first sending 4 and then sending 17, but of course, due to function composition, it's really the other way around. Here, this is sort of looks like an imperative style. So here you can see I'm using the borrow notation in order to grab the first prefix here of the channel, send 17, send 4. And here you can see that this really nicely scales if we have more than one channel. So both of them are represented by borrows. Int return, send a bool return, and then I can just use these channels in any order whatsoever. And you can see here already some benefits of that. And we claim that this is a more modular style because you get rid of this resource passing. You are not forced into a particular programming style. You don't need to waste polymorphism on something that doesn't need it. You can use it for more interesting things. And it's also much, much easier to return values. I mean, here it's always unit because I'm just sending stuff, but you have a slot there where you can return something and it doesn't get cluttered with having to return resources. Let's talk a little bit about ordering, what I promised you before. Suppose we have a channel of this style, first send an integer, then send a bool, and now let's take a borrow of that channel, right? So let's take the first communication plus return, let's take that as a borrow. So now, after doing that, our context looks like this. We have x bound to send int and then return, semicolon, c bound to send bool and then close. And the semicolon will turn out to be the important thing. Namely, if I now try to extend the program by sending true on c, we get a type error, because the semicolon advocates that the binding for x must be consumed before the binding for c. Yeah, so the binding for c is not available at that point. So what you have to do first, we first have to act on x. So then this binding for x is consumed by the send. Afterwards, it's gone, and we can further on consume the binding for c. Now, what's the secret sauce behind the semicolon? That's called BI context. So we're using BI context and ordered and unordered composition there. So here we have the semicolon, that's ordered composition, and it means stuff that is bound in the left gamma has to be consumed completely before stuff that's bound in the right gamma. Whereas the normal one, which I'm writing here as with this parallel symbol, that's just the normal composition for linear bindings, and you can reorder them in any way that you like. Now, this is the story. We had a similar story last year already in a paper about type state. So this is good enough for the sequential part. But now we have the session types. We have to worry about concurrency too, right? I mean, that's the point of having session types. So let's have a look at a very small program where we want to try to do borrowing across threads. Now, so again, we have a protocol that has two interactions so that it fits on the slide. But now we're doing a first borrow that happens from this channel that happens inside of a fork. And we're doing a second one that happens in the continuation. Now, how do we enforce that things actually happen in the proper order? Right? I mean, the type system has to make some decision. Maybe it's naive and says, this one is the string is the int borrow, which would fit with the typing, and this one is the string borrow. But we have no way of enforcing that, right? So the execution of the threads here that can happen in any order. So what do? Well, we change the representation of borrowed channels so that the splitting that happens in the moment we take a borrow, that attaches some sort of synchronization to the ends of the borrowed channel. So essentially what happens is if we are finished with the borrowed channel, then we are actually handing off ownership of the underlying primitive channel to the next guy down the line. Yeah, so essentially when we're doing this receive here, in addition, we are dropping the channel and passing on the underlying communication, primitive communication channel to this next receive. So how does that happen? That happens in our paper by performing a transformation, or in a compiler that would do the transformation. So essentially what we're doing is we're representing a borrowed channel by a pair of cells. So, and the first cell here is really one end of a one-shot channel, and on this one-shot channel we are expecting to receive the primitive channel on which we do the actual communication. That's maybe a bit, let me show it to you in a picture. So that's the typical representation of such a borrowed channel. So here what color is that? Yellow or whatever, orange. So this part is the port, the cell on which I expect to receive the primitive channel from the left, from a borrow, for example. And so when I want to do any action on this guy here, I have to wait so that I get the primitive channel from the left. Then I can do whatever I want. Usually I do just some primitive operations on them. And when I'm done with that, I have to hand off the primitive channel to my continuation. Yeah? So I always push it back into this blue part, which means when I take a new borrow, yeah, so when I say, so this here stands for R, when I split this further up, all I have to do is, like here, I have to insert a new cell so that when I'm finished here, I'm not pushing directly to this guy here, but I'm pushing to this intermediate cell, and then this subsidiary continuation can pick it up, and once that is done, it passes it on to the final part, to the final continuation. And I'm not going, due to time reasons, I'm not going to show you the translation, so there is a nice picture in the paper that also serves as the proof of the type preservation of this translation. So what do you find in the paper? So we are presenting a type system for session types with borrowing. As you have seen, heard, this is based on our version of ordered types. The way we implement it is we are doing a type preserving translation to a version of GV with priorities. And the reason why we do that is this translation yields type soundness, so we don't have a separate type soundness proof. And it also yields deadlock freedom, because the system priority GV is guarantees deadlock freedom. The nice part about that is our translation that introduces all these intermediate cells and extra communication doesn't introduce any deadlocks, despite even if we do it in a strongly sequential part. So moreover, we have a mechanically verified artifact in ACTA, and we have an implementation with practical extensions, and you can find all that in the artifact. And that's what I wanted to say. Thank you.
I think we have time for one question.
Thanks, Peter. So it seems like nice work. I'm still a bit confused. In the example you gave where you forked off this thread, how does the type system know to do the splitting? I mean, how does it know that the forked thread goes first?
Good question. So the type system just makes an assumption about that. So it would just split it according to the occurrences in the text, and then this mechanism, the synchronization mechanism, kicks in and makes sure that this actually gets enforced at runtime.
Okay, so it's just left to right in the text.
In this case, It's sure. In this case, it's just left to right. Yeah.
Okay. Thanks.
Yep. Good.
And now up is Wen Hao to talk about modal effect types.
So hi, I'm Wen Hao. I'm going to talk about modal effect types, which is joint work with my collaborators. Okay, I'll start with a recap of traditional effect types. So what are effects? There are many different descriptions, and my favorite one is that they are the way that programs interact with the environment. There are many examples like I/O concurrency, exceptions, and effect types statically track the use of effects in types. So let's see how traditional effect types work. Here is a very simple increment function that takes x and increments it by 1. And another simple higher order app function that takes the function f, takes parameter x, applies f to x. And if we apply f to inc to 42, we get 43, which is basic functional programming. The idea of traditional effect types is to annotate each function arrow with the effects that they use. So here we have these empty braces beside each function arrow, which mean empty effect, because these functions are pure. They are not doing any effectful computation. If we change the definition of inc to call an operation ask, which takes a unit, returns integer. Intuitively, it asks for an integer from the context. We need to track the usage of ask in types. So now it is a function from int to int, which performs ask. And in order to apply this higher order function app to inc, we also need to change the type of app to allow the argument to use the effect ask. And in general, in order to be able to apply app to any effectful function, we need to use an effect variable e to abstract over which effects can be performed. And since the argument f is also used in the definition of app, other arrows of app also have this effect variable e. Similarly, for inc, we also need to add an effect variable e in order to be able to use inc together with other effects. And here is a handler for ask, which takes a function argument and handles the ask operation of it by assuming the continuation r with 37. For the type of the argument, we have ask and e, which means this is the function that might perform ask. This ask operation is handled by the handler here, and it may also perform other effects e that is abstracted. So we can apply this handler to arbitrary effectful computation that may perform ask. So this is the basic idea of traditional effect types. As we can see, there are many effect variables like e almost appearing on every function arrow. This is especially painful if you want to add such a system to existing languages, because there are already many type signatures of higher order functions in the library code, and we need to change all of them to add these verbose effect variables. So the question is, can we get rid of these effect variables? And we propose modal effect types to solve this problem. So let's take a closer look at the definition of app. It is a rather simple function, but has a very long type signature with these verbose effect variables e. And this is unfair because app itself is an innocent, pure, higher-order function which does not perform any effects at all, why do we need to add these effect variables to the step signature? Why don't we just track the fact that its definition does not mention any effects? But however, we can't do that because in a traditional effect system, we have to annotate each function arrow with its effects consistently. So our idea is to decouple effects from function arrows. And the key concept for decoupling is ambient effect context, which is tracked by the typing judgment, which means the effects that are provided by the context. So here we have this app function, we have this @e, which is part of the typing judgment, which means that the context of this function provides effects e. And effect context propagates through the whole program. So for the argument function and the result function of app, their effect contexts are both e. In order to have some effect information in the type, we use modalities. The first one is the absolute modality, written as a square bracket with f, which means that for the program inside this modality, their effect context is f. So for app, since it is pure, we can use the empty square bracket to mean that we can use the empty square bracket, assuming the ambient effect context is e. This modality overrides e to empty. So we know that for this function inside, it is pure. Its effect context is empty. And we have a natural notion of sub-effecting, so that although f is a pure function, we can of course use it under any effect context e. Similarly, for ink, instead of having this quantifier of e and adding it to the function arrow, we can use an absolute modality to say that the definition of ink uses ask, and we do not care what other effects that might be used when we apply ink. By sub-effecting, we can still apply ink with other effects. We also have relative modality, which is in particular useful for handlers. So this is the handler for ask. It is a higher order function, as we have seen before. Takes the function, handles the ask operation of this function. With relative modality, we just need to specify which operation is handled by this handler. So assuming the ambient effect context is some effect, is e, this modality adds the operation ask to the effect context e. So for the argument, its effect context is ask and e. This ask operation is introduced by this handler and is handled inside this function. So the outside context is still e. Yes. And of course, as itself is a pure function, it handles ask, but its definition does not use any actual effects. So we can also add this empty square bracket to keep the information that ans itself is pure. And by sub-effecting, we can apply ans to arbitrary effect for functions that might perform ask as well as some other effects. So this is the basic idea of modal effect types. Instead of having some quantifiers and effect variables, we use these succinct modalities to track effects. And we have the convention that global definitions implicitly have an empty square bracket because global definitions should be pure. So the types becomes more succinct. And we can of course compose them together. There's one example of applying app to ink and handles it by ans. And here is a more complicated example about cooperative concurrency. I'm not going into the details, but I'll just show the animation of the change over types. Yeah, and now I'll quickly introduce the first typing rule, which is modality introduction, to give you a flavor of how the system works. So we have this mode syntax, which introduces the modality for the result type and a knock to the context. And it overrides the ambient effect context E to ask. These knocks are used to control which variables can be used. So this is the usage of the variable. And we have these modality transformations to allow this variable f to be used after a knock. And in order to have such a variable binding like f, annotated by some modality, we use modality elimination with the syntax net mode to eliminate. Here we eliminated the modality, the empty square bracket. Yeah, and there's more in the paper. We have a call calculators based on multimodal type theory inspired by Frank and effect. We also have masking. So our previous relative modality only adds effects to context, but we can also remove effects from the context. And standard meta theory, some extensions like standard polymorphism, algebraic data types, and a simple bidirectional typing, and some encodings. Yes, and we have an artifact, a prototype implementation. So there are also some ongoing work about a framework for encodings, and we are doing better type inference. I want to have a formal comparison with some with capture tracking, and also like distributional semantics and higher order effects. So I think my takeaway is do not track effects of function arrow. Instead, track them when needed and track them with modalities. Thank you.
We have time for some questions.
This looks really cool. I was just wondering how things behave then when you're doing sort of lambda abstraction.
Mm-hmm.
Am I right in thinking that essentially the modal context of the body is just the same as the modal context
Yes,
of, yeah?
Exactly.
Okay,
Yes.
so it's a sort of contextual style effect.
Yes.
Yeah, okay,
Yes.
yeah, that makes sense. So it's not like captured inside.
Yes.
Yeah.
Yes, so function by default do not do anything to the effect context. And the effect context is only changed when we introduce modalities.
Right, great. Okay, thanks.
Thank you.
Hey, so Scala 3 does something similar with capabilities.
Mm-hmm.
Can you compare it a little bit with that?
This is one of the first work that I'm listing here. And we have compared between effect, which is a research language with capabilities, and our work, but we haven't do the comparison with Scala, and I want to do that.
Okay.
It seemed like you added the mod expression constructor. Could you go into that a little bit more?
Sorry, could you say again?
You had also a new expression term, which was this mod thing, I think it was called.
Yes.
Could you go into that a bit more about what that means? Besides how the effect on the types, like how is it, does it have an operational effect, or is it just a type effect?
Oh, well, it is just an explicit syntax for introducing modality. It is very similar, like if you think of system F, it also has this big lambda alpha, which is an explicit syntax to introduce a type variable. And here, what's happening is very similar.
So it's sort of like a mini type annotation in a sense.
Yes,
Okay.
you can understand it.
Okay, let's thank Wenhao again. And now we have Taro to talk about higher order model checking.
Okay, so yeah, thanks. So today I want to talk about some extensions of higher order model checking to effect handlers. So first, let me explain the higher order model checking, which is extensions of the model checking to higher order programs. So in this framework, so system is described as some higher order programs yielding trees, like the higher order recursion schemes and the PCF terms. So the properties to be verified is a predicate over trees. And for example, it can be a monadic second order logical formula, modal mu calculus, perhaps something like that tree automata. So then the higher order model checking is a problem to solve whether the trees yielded by the program M satisfy the formula 5. So this is a very rich framework, and it can express various verification tasks like the safety and liveness verification, including the assertion checking and termination analysis. Okay, so let's see one examples here. And here the program M defines a recursive function f, and within the body, it first executes a non-deterministic choice star. And if it returns true, then the close operation is called. Here the open, close, read are some file operation, and I suppose that file resources are maintained globally in the backend. So close is called if the non-deterministic choice returns true. Otherwise, the first read operation is executed, and then the same process are repeated. And the main program first opens the file, and then recursive function is called. So first, by executing this program, first operation open is executed. So the generated trees, root node of the generated trees is that open node. And then the next non-deterministic choice is executed. So the next node is that non-deterministic choice here. And if okay, sorry. Yeah. Okay, so if it returns true, then close is called, and otherwise read is closed, and then the recursive call goes to the recursive call. But first, again, the non-deterministic choice is called again and again. So this is trees generated by this program. So then, for example, if the properties we want to verify is that is there no infinite path. So it means that this program may be non-terminating. So of course, in this case, this property doesn't hold, because if non-deterministic choice always returns false, then the program is diverges. And if we want to verify these file operations are used in correct order, so then this program satisfies these properties. Okay, and recently this higher order model checking is extended for effect handlers. And effect handlers is programming features to implement control flows, like the exceptions, coroutines, and backtracking, and more. Okay, so this is one simple examples using the effect handlers. So here, the first 3 lines define the effect handlers, and actually it defines the effect operation this side here. And the program starts here in the handled expression. So first, open operation is called, and next, okay, so then the generated choice is start from the open again. And here, next, decide operation is called, and this is handled by the effect handlers here. And so then the control goes to this close, and here decide operation close takes not only the parameter x, but also takes the continuation k here from the point the decide is called. And in this close, the continuation is called by the argument true. It means that this decide operation returns a true. And then the string A is chosen, and the write and close operations are called. So this computation tree is generated. And of course, this trees satisfy the property, so model checking will be success. But if the decide close, here I modified the program to call the continuation twice here. again k holes. Then after calling the close, control go back to the decide close. Then the second continuation call is executed. So then the continuation starts from the decide operations. So decide operation returns false here, and then B is chosen, right, and close are called again. So then the generated trace is something like this one. So then the properties, the correctness of the file operations doesn't hold for this one. Okay, so this is how we can extend the higher order model checking to address effect handlers. But the problem is that the higher order model checking problem with effect handlers is undecidable. This is because if under a higher order model checking without effect handlers is decidable. This is because the effect handlers are very expressive, and actually they can encode natural numbers. And it's well known that higher order model checking becomes undecidable if the programs can use the infinite data domain like natural number. So then the higher order model checking in the presence of the effect handlers becomes undecidable. Yeah, but then the natural question is that what's a fragment where the higher order model checking is decidable? So how we can restrict the programs or effect handlers and so on to make the model checking decidable? Okay, so our contribution is to identify some class of the higher order programs where the model checking is decidable. And in this class, there's no restriction on effect handlers and no restriction on effect invocations if the invocation is handled by the tail resumptive effect handlers. So tail resumptive effect handlers takes this form here, this specific form, where continuation k can be called only at the tail positions. So if we consider only these effect handlers, then there is no restriction on effect handler. But otherwise, if some effect handlers are not tail resumptive, we need some restriction. And in this work, we restrict the interpretations of effect handlers can rely only on some statically bounded number of the non-tail resumptive effect handlers. And okay, so this is theoretical contributions, and another contribution is on implementation. We have implemented a higher order model checker for subset of the OOPSLA, and it checks input programs that belong to this class, and if so, then it model checks. Okay, so let's show me the examples, what programs are accepted in this, belong to this class, and what does not. Okay, so first, I presented two examples I presented belong to the decidable class we proposed. Because in this case, only one effect handler is used. So of course, use the effect handler, the number of the effect handlers are bounded. So no problem in this case. So the problem may happen in the program that uses potentially unbounded number of the effect handlers. So here I define the recursive functions, and this recursive functions installs new effect handlers for each call. So here, first, these examples are called non-deterministic choice. Okay, so here are all operations, including non-deterministic choice and right are handled here. And the first non-deterministic choice is called, then it handled by here, but it is forwarded to the outside. And then the result is given, then the continuation is resumed. So it is just a forwarding the operation. Okay, and then if the non-deterministic choice returns true, then raise operation is called. And this is actually this handler only handles the raise exception, so it's something like that exception handlers. And if the choice returns false, then write operation is called, and then recursive call is executed. And in this example is belongs to the decidable fragment. So because raise is handled by the nearest handler, so the interpretation, the only one handler gives the interpretation to raise. And star and right are only forwarded, so forwarding clauses are tail resumptive, so no problem in this case. And of course, we can change the argument and return the value from the operations. Then this case also is decidable. But the problem happens if we want to manipulate or continue some computation after invoking the continuation. Okay, in this case, this example is outside of our class. So then we cannot answer for decidability question. Okay, so formalization, first we have two languages, and first ePCF is a simple language. It's similar to the PCF, but only finite data domains are available, and we also support algebraic effect here. And the other one is that extensions of ePCF with effect handlers. And we defined a class, decidable class using a type system, and which support some answer type modification, answer type polymorphism. I don't explain the detail, but these two features are very important to bound the number of the handlers and allow the unbounded number of the handlers if they are tail resumptive. And then after defining the fragment, we define the CPS transformation from this fragment to the ePCF. And the higher order model checking in ePCF is decidable. So we show that this fragment, the higher order model checking for this fragment is decidable. Okay, so last I want to mention about the implementation work. So our implementation is integrate takes the HEPCF program without annotation. So first implementation does type inference, and then the CPS transformation to the ePCF term. And then we use backend or higher order model checking tool for the CPS transform terms. And we just tested our implementation for a small benchmark, so the verification completed in less than 0.2 second, but its benchmarks are very small, so we need to more larger scale the benchmarks to test the actual performance. Okay, so yeah, that's all for my talk. Thanks.
We have time for some questions.
I have a small question about this very slide. In this, when you say K of uppercase M, what does the M range over? Is it a value or is it an arbitrary expression? And then will it be executed there, and then the result will be?
Yeah, M is an arbitrary expression. So
okay, and you can't resume with a computation with a.
Yeah, right. So including the effect invocation and the effect handling, arbitrary expression is it.
Because that would make it undecidable, or if I mean if you could send some computation back to where the effect was raised and then force it there.
You mean that if the M, sorry, could you?
Or we can discuss this
okay.
offline.
Okay, let's thank Taro again.
All right, hi. I'm very excited to talk to you about information flow today, specifically type systems for information flow. Okay, what do information flow type systems do? Fundamentally, their purpose is to track the dependency structure of your program statically. And so if I'm holding a computation in my hand, I want to know exactly which bits of data that computation depends on. Okay. And this is super useful in a domain like security, right? Because I want to say that computations that depend on password information are not allowed to leak things to the internet, or they're not allowed to print things, right? But it's also useful for these data provenance and separation properties are also super useful for things like concurrent and distributed systems, right? And also for like program slicing and build systems and incremental computation, and surprisingly controlling unfolding in dependent type theory. And also I found out 2 days ago, lineage tracking in CAD kernels, and also like many, many more things. So I'm going to take the security perspective in this talk because I think it's a particularly simple one to take, but I think it's helpful to keep in mind that information flow and dependency tracking is a broadly useful technique for lots of PL stuff. Okay, so I want to walk through how to reinvent our approach from scratch, basically, starting with parametric polymorphism. So if I give you the identity function, the standard polymorphic identity function, you know that the argument to it flows exactly to the return value, right? And if I give you this second function, you again know that the first argument to it flows exactly to the return value and that the second argument is ignored. And if I give you this map function on lists, right, you know that the elements of the input list flow to the input of the higher order function argument to the list, or to the map function, and the return value of the map function flows into the elements of the output list. But what about something non-polymorphic, like inker going from int to int? So our first insight of 3 is to separate data abstraction from information flow properties. So we want to weaken parametricity to separate out the part of it that talks about information flow properties. Okay, and the idea is to tag types with dependency variables alpha. So instead of having alpha be the type, we're just going to have them sit next to the type. And so our type for inker is alpha int to alpha int, and the alpha plays the same information flow role as before, but not the data abstraction role. What about something like the addition function on 2 integers, right? Here we have 2 separate dependencies flowing to the same return value, right? So how do we indicate the 2 dependencies on the return value there? And our second insight is to generalize from individual dependencies and types to sets of dependencies and types. Okay, so we're going to take each alpha and turn it into a dependency set alpha. And so we get this new signature for add that takes an alpha int to a beta int to an alpha beta int, where the return value here says, this is an integer that depends on data from sources alpha and beta, so it depends on both of the arguments. Okay, so let's do a more interesting example now that we've got some tools. Okay, we're going to start by declaring a variable pass that is a string initialized to the name of my cat, where the type declares that this string depends on or is password data. It represents password data. And we're going to declare another function, check, that takes in a password attempt as a string with dependencies alpha and returns me a Boolean with dependencies alpha and password. And these dependencies make a lot of sense because the body of the check function just compares the password attempt, which has dependencies alpha, to the pass variable, which has dependencies password, right? So you end up with 2 dependencies on this Boolean, which are exactly the 2 involved in the body. But to some extent, this checker is too conservative, right? Because if our policy is that we're preventing things that depend on password data from printing or leaking into the outside world, we can't actually return the result of the password check to the user, right? Because the type system will say, no, that's insecure, you're leaking data about the password. And so I'm oversimplifying here, but the solution to this is something called declassification, where you insert basically a cast into the program that says, I'm going to take a computation that is said to be dependent on this password label or this password dependency, and declassify is going to peel off the password dependency, and it's going to return the exact same computation to me. And this gets us the type signature we want, right? Because now we're doing the computation we want without the dependency we didn't want. But this is kind of unsatisfying as a PL person because this is just an unsafe cast, right? Again, I'm massively simplifying, but at its most basic, it's some kind of unsafe cast. And there's this very conventional wisdom, that non-interference, which is the core soundness property of information flow, which says that basically dependency tracking must be fully faithful to what the program actually does, is sort of in conflict with declassification. It's in conflict with writing practical programs. So if you look at the Wikipedia page on information flow, it just says this outright, right? And to use a better source than Wikipedia, there's this wonderful paper by Sabelfeld and Sands from 2007 that says, you know, this password checker program that we want to write is not possible under a fully strict non-interference policy, right? But I want to advance the perspective in this talk that non-interference is really a far more practical property than a lot of people give it credit for. And actually, using just the tools we've already introduced, it's possible to obtain the password checker that we want, which is a little bit surprising. So let's go through it slowly. So how do we get declassification for free, so to speak? And first, we're going to do some wishful thinking. So ideally, we want something like a password checker module. And what that module is going to do is it's going to declare a password dependency. And it's going to have a string field that plays the same role as before, pass, which is tagged with the password dependency. And when we use it in this usage here, and we like concatenate that password field to some other string, we end up with another string that's dependent on password as expected. We have this check function where the Boolean return value now is not dependent on password. And maybe we also have this encrypt function that takes in a password-dependent string and encrypts it and returns us a string that is no longer said to be dependent on password data, right? Seems reasonable. Okay, the first step of getting there is to expose some lurking quantifiers. So when I showed you the type of the signature of the polymorphic identity function, right, I hid the quantifiers from you. But really, there's this for all alpha sitting in front of the type signature that binds the alphas in the type signature. And same thing for the map function, right? There's these for all quantifiers sitting in front of the signature that bind the alpha and the beta in the type signature of the map function. And when you graduate to doing information flow, it's the same idea, but instead of quantifying over types, you're instead quantifying over information dependencies, right? So these quantifiers bind the information dependencies, alpha and beta, in the signature of add. So our third and final insight is to take universal quantifiers on higher order functions and smash them together using the Girard encoding of existentials, which I won't explain, to get existentials. And the core insight here is that you've already sort of seen existentials in probably most languages you've used. They're roughly just modules or classes with a lot of asterisks, but like roughly. And so let's briefly review how modules work. So we've got this Q, which seems to be a popular data type here. And this type T in this Q module can be thought of as some existentially quantified thing. And from the client's perspective, it sees, you know, just the type exactly as I've listed, right? So the type T sort of represents some particular Q, and you can use these NQ and DQ functions on that type T to like either string elements into the Q or extract elements from it, right? So this is familiar if you've used ML modules. But the signature that the implementation gets type checked against is the version of that signature where you substitute in for each occurrence of T in the signature this list T implementation type that is used by this naive Q structure implementation in the bottom, right? So its NQ and DQ definitions will be type checked against that substituted signature. So just to go back and forth once more, there's the client view, there's the implementation view. Okay, and it turns out that gives us basically exactly what we need to implement the signature that we wanted. So let's start implementing. And our first and really only interesting move is going to be to set the password dependency in the implementation to empty, right? And this is a valid move because when we generalized from individual dependencies to sets of dependencies, we made it so that each individual dependency variable in our type system stands for another set of dependencies. So this is a fine thing for us to do. And namely, when we do that, we make it so that from the perspective of the implementation, each occurrence of the password dependency in all the signatures of the password checker module are crossed out, they're elided, so the implementation doesn't have to care about them anymore. And so we implement pass again exactly as we did before by setting it to the name of my cat. We implement check exactly as we did before, where we just take in an attempt and compare it to the password field. And now check can just return a Boolean because note that password does not depend on the password dependency, right? From the perspective of the implementation again. And we can implement encrypt as just the ADA expansion of this GPG function, right? Because from the perspective of the implementation, what you're really implementing is just a function from alpha string to alpha string, and that's a really easy signature to inhabit. And I want to sort of declaim here that, like, of course, you could implement some totally insecure function that just like leaks the entire password, right? You could export like the identity function from this thing, and it would just leak all the data, right? But the point of this technique is that if you want to do that, it has to be part of the abstraction of the password checker module. Like some random client of this thing is not allowed to do that. So there's this very nice modularity and composability going on here that's very familiar to statically typed programmers, right? And importantly, this all emerges just from those 3 insights we had. And I haven't added any of this to the language. This is purely just from those sort of totally uncontroversial insights. And that's sort of the bulk of the work, but I wanted to note one last thing, which is maybe actually familiar to those who are here for the modal effect types talk. We have this heuristic called dependency elision in our language that makes it so that when we can use these incur and add functions, or when I type these incur and add functions, I listed these dependencies on them that are kind of extraneous, right? They're not necessary because most functions use all their dependencies. And dependency elision is a recognition that, you know, maybe we don't have to list those like sort of boring dependency chains in our type signatures. And so when we write these sorts of functions, we can just elide them, right? And when after sprinkling on just a little bit more proof theory, it turns out that we can write the types of the map and fold functions on lists exactly as the bog standard types in our language, but without losing any precision in information flow tracking for special reasons. And filter is almost the same, but you have to have this beta tag on it. And the full explanation for why we can do that, and like a lot more really interesting tidbits are in the paper, so you should go read it. But the takeaway really is that, right? And I'll take questions.
You have plenty of time for questions.
Hi, thanks. This is a really cool talk, really cool work. I'm a little bit curious what the actual non-interference guarantee you get out is, because it's not going to be the standard one. It's going to be non-interference up to some module boundary stuff, right?
It's actually, so if you look at our logical relation for non-interference, it's actually, if you remove the case of the logical relation for alls, it's exactly the same. All the declassification stuff is handled in combination with the case for alls and the case for function types, and our paper steps through basically the inner and outer perspective of the existential encoding, and shows how from the inner perspective you just assume that the implementations of these module signatures preserve non-interference, and from the inner perspective you like don't see the password dependencies, or you don't see the existentially quantified dependencies at all, so it's not relevant to non-interference.
Okay, very cool.
Thank you for the good talk. We've talked about this already, but I just want to hear your thoughts again about what other kinds of applications is there for a type system like this?
What other kinds of information? What other kinds of applications there for information flow?
Yes.
So a lot. I have a text file with a very quickly growing list of them, but one of my collaborators, Will Creighton, pointed me to this great page on the Svelte documentation, which is this reactive programming library for JavaScript, where it says, you know, if you do a reactive update inside a closure, the Svelte analysis is not sophisticated enough to realize that a reactive update actually has to fire. So the recommendation of the documentation, at least when I looked at it a few months ago, was to go outside the closure and like do a self-assignment, do like an x equals x, to get it to realize that there's a dependency being induced, so a reactive update can fire. So if you don't do that, you're gonna have a dependency analysis bug. Also, if you have an information flow type system helping you with this reactive programming thing, you can compile it like way more efficiently, right? Because you don't have to do any of this like shadow DOM or tree diffing or any of that, right? You can just like make it so the compiler compiles your program such that when you touch some data, it like statically knows exactly what other data to reactively update. That's one really compelling example. All the credits to Will Creighton for that.
Okay, thank you.
Excellent talk. So I wonder, I think you have a dependency set. Is it associated to each argument or to each type?
Yeah.
So for example, if you have a function that takes a pair, like a pair of A and B, do you have a dependency set for A and B, or do you have a dependency set for the whole pair?
That's a really interesting question. So we connect the granularity of dependency tracking to something called polarity from proof theory. And so we support positive pairs in our language, or we support positive products in our language. So by default, like the dependencies of pairs are tracked coarsely across the entire pair. But you can choose yourself to give yourself negative products by just using the usual encoding, and then you're forced actually, because it's then a negative type, to track the dependencies individually for each projection. So it depends on the polarity.
I see. Thank you.
Yeah.
Okay, let's thank Hemant again. we have Jirka on simple essence of overloading.
Hi everybody. Today I'd like to talk to you about our joint work with my advisor, Jonathan Wachthuizer, about distilling this simple essence of overloading. First off, well, what is overloading? Let's look at an example. This function takes x, an argument, and calls show on x plus 1. But, well, what is the x, right? Is it addition of integers? Is it addition of strings? I hope not. Is it addition of two vectors of size 2 of integers? Perhaps. So the goal of overloading is to resolve unqualified ambiguous names into qualified names based on the type context, at least for this talk. So the most commonly used implementation strategy and part of the theory is just using backtracking. This is the same example, it's just ANF'd for, well, we'll figure that out later. I'll explicitly write those two overloaded names here with the two overloads. And let's start the inference process. So we start at y is add of x plus 1. And we say, oh yeah, it's addition of integers, because that's the first overload we have. We deduce that x and y have type int. And then we move on to the second line of the program. We take the first overload for show, which is showing of strings. And we get that y is a string. Wait, what? I thought, what? OK. Now y is supposed to be an integer and a string, so that's a contradiction. And this is exactly where we need to backtrack. So we go back. This is fine. Let's continue. Take a different overload for show, this time one taking an integer, returning a string. And, well, this works out. So we're done, right? Well, except we're not done yet. Let's look at a table of all of the solutions. We've only seen the first row, so we've seen addition of integers, but we haven't actually tried everything. And we want our overloads to be unambiguous, therefore there has to be exactly one green tick. So we do need to check all of the combinations. Now, I'll claim that backtracking is somewhat anti-modular. Here's a type checker pipeline. We gather the constraints, solve them, and then continue. And when we add overload resolution via backtracking, something weird happens, right? The constraint solver can fail. Bad overload, it's so over, going back to the constraint gathering, which then can find a new overload claiming that it's so back. Even worse, we as language implementers need to implement our type checker state so that it's snapshotable and restorable. And there's been at least one paper doing the exact thing I'm talking about. And for the programmer, this is very hard to reason about, not to mention the error messages. So to call back to a previous talk, I reject the whole premise of this. What I want is to have modular overloading, to have this beautiful blue box that takes the result of constraint solving, does some magic, and resolves everything without me needing to change constraint gathering or constraint solving too much. So let's try to analyze the program again. This time, I'll ascribe type variables to x and y. And we notice that the argument x flows to the first argument of add. Now, let's do a little bit of wishful thinking. If addition is the addition of integers, then alpha flows to int, right? If we know the solution, then we know the flow. But if addition is addition of strings, we have a flow of alpha to string. And by the way, if you're scared of the inequality constraint, just imagine an equality, it's fine. We can also draw this, so there's a conditional flow from alpha to integer if we chose the addition of integers, and from alpha to string if we chose the addition of strings. Okay, let's continue with the constraint gathering. I'll build up the graph so that we can see it. I'm simplifying flows through functions to make the diagram slightly more digestible. And again, there's a flow from alpha to int if we choose add int, and a flow from alpha to string if we choose add string. Note that the constraints we get are variational. The constraint only needs to hold if the condition above it is satisfied. Now, we can continue with the flow from the second argument, the literal one. If we choose addition of integers, then there's a flow from integers to integers. If we choose addition of strings, we get a flow from integer to string. And if you find this particular flow weird, well done. But let us proceed for now. OK. Again, if we choose, here we flow into gamma, into y. And if it's addition of integers, then it's a flow from integer. If it's addition of strings, then it's a flow from string. Now, finally, let's look at the input of show. So if show is showing of integers, we have this flow from gamma to int. And if it's showing of strings, well, it's from gamma to string. Now, I'm sure you believe me that the diagram is quite beautiful, but it doesn't actually help us solve overloads yet, right? Let's get back to the strange inflows to string constraint where add string is chosen. Now, using a many worlds interpretation, discovering such an invalid constraint tells us that the worlds annotated on the constraint are invalid. Therefore, we know that addition of string is a bad choice. Unless, well, int is a subtype of string, but please don't make systems like that. There's also a bad transitive flow from integer to string via gamma. And notice that this disqualifies all of the world where addition of integer was chosen, and at the same time, showing of strings was chosen. Similarly, there's one more transitive invalid flow from strings to integers in worlds where we choose addition of strings, and at the same time, showing of integers. Now, instead of having this weird side table on the right, let's incorporate this into the program itself. We have a core calculus, originally from variational types, which were used to model software product lines. And for each overload, we have a fresh dimension, though in general they don't need to be fresh, and each has alternatives. From this, we gather the constraints to build a variational constraint graph, and it doesn't need to be a graph, just a list of edges is perfectly fine. And we get variational error constraints. So when your constraint solver fails, and it failed in some specific world, we see which descriptions of worlds are invalid. Now that we have the invalid world combinations, we can try to characterize all of the valid worlds. Now, valid worlds are all the possible worlds, so exactly one assignment per dimension. And at the same time, there can't be any invalid worlds. So not the first description, not the second description, not the third description at the same time. And now, as a reminder, we want to find an unambiguous valid world. And as a consequence of having this beautiful modular description, we can take a solver, like a BDD solver, for example, but I'm sure you all can find much better solvers than I could. And we plug this equation in and get very quickly out the number of assignments and the single valid one. Now, you might be asking, is this even practical, or is this just for your warm, fuzzy feelings? Well, it's straightforward to implement this. We did it in Rust. We compared performance to Swift, where Swift uses a Hindley-Milner style type system. It uses a constraint-based system, and it has overloading, and it's a production language by a big company. And comparing to Swift, we can see that we're at least practical, though we found some fun examples of encoding return type overloading, where Swift times out after 9 minutes, telling the user to please split their expression. It scales quite well on artificial benchmarks, at least. This takes an argument and adds it together n times with m different overloads for addition. And it scales quadratically in each dimension. And finally, if you're not convinced by this, we also have a web playground. So you can go ahead, type up exactly the example I've shown, change it, and see how you manage to break the system. Now, in the paper, there are many more examples. There's a description of how to apply this for both a Hindley-Milner style type system and algebraic subtyping. We have a formal description of the system and its meta theory. Choices can have arbitrary expressions inside, which might be fun for something like UFCS. There's slightly more descriptions on many worlds interpretation with a modal context, and we tell you how to encode this into a binary decision diagram. So the simple essence of overloading is that it's a flow-based, practical, modular way to infer type-based overloads. Thank you for your attention.
We have plenty of time for questions.
Hello, thank you for the amazing talk. Do you have any plans to scale this to an ML system with local let generalization?
Thank you for the question. Currently, we were not planning on supporting local let generalization as is. That's also, there are many authors of papers who do claim that if you have a function which takes, let's say, a person and return person.age, this should be generalized into some great type which tells you for everything alpha that has an age, this returns a beta where the beta is the age. And for now, at least for the very simple essence, we've decided to not do this.
Hey, thanks for the great talk. Have you compared this to Haskell type system and its type classes? Because to me, I don't see the difference between these two. And they've solved it without using an external modular solver, just by you doing inference.
Yes. There are two cases, I think, in which you might want to use overloading. One is you already have overloading, like most production languages, unfortunately, and want to get out of the mess you got yourselves into, 20 years ago. Or in the case of Swift, like 8. That's one use case. The other is we can guarantee, this happens during compilation, so we can guarantee there are no dictionaries being ever passed around, and we don't need a single principal type. So for example, Rust plans to add variadic generics in order to support like addition of 2 things, 3 things, 4 things, 5 things. And here we can do it in a sort of unprincipled, very local way.
Okay, thanks.
I think my question was the same as his, which is, right, type classes are very popular as a way of dealing with overloading. And main languages have them, like Rust has them in the form of traits. So can you play nicely with type classes and get both?
Yes, I certainly hope so. I haven't tested it out, but there's nothing that would indicate that it's not possible. And Swift does this. Swift has both overloading and type classes.
Right. Except they don't call them type classes, they call them protocols.
Yes, that's true.
Okay, thanks.
Thank you.
Do you have a general complexity bound for any programs? So you have a specific example, but in general, static overloading is NP hard by reduction to free set.
Yes.
So.
Yeah, exactly. One of the benchmarks is even, I need to go through all of the beautiful build-ups. One of the benchmarks is called 3SAT, and it's exactly Eric Lippert's encoding from 2008 when they added delegates to C#. And yes, it's NP complete, and this is partially because of return type overloading. And there's just not much you can do about that.
Okay.
Thank you for, if I was being mean, I'd say thank you for an interesting ICFP talk. This question is dubious in more ways than one, which is that at OOPSLA there was a paper which pointed out, I think it was by Todd Milstein, that for multi-methods, which is to say almost dynamic multiple argument overloading, you can't be modular and symmetric. And what was the other clause? Modular and symmetric. Certainly you can't. And there was something else. Oh, I can't remember. Basically, it says there's a result there that this is something you can't do, but you seem to be doing it or something very close, because you're claiming to be modular and presumably symmetric. And
I would be very interested in talking later about the paper in question, because I don't exactly see the problem you're describing, but I would love to know.
I guess it is that possibly what you're using by modular, which means no backtracking in the inference algorithm, if I could talk about what you said, whereas their definition of modular means you can't cause overloading resolution failures by adding other modules.
Yeah. Okay, thank you. We can talk later. I'm very interested in the paper.
Okay, let's thank Jirka again. And the last talk in the session is Patrick about type-guided repair.
Okay, hello. My name is Patrick LaFontaine, and I'll be presenting our work on type-guided repair of incomplete input generators. So I think we would all like our code to have less bugs in it, but unfortunately we do not necessarily write enough tests to exercise all of these bugs. So one alternative is to use probability-based testing. It's an automated testing strategy. It comes in a variety of frameworks in basically all of your favorite languages. So as our motivating example here, I have an OOPSLA function in QCheck, which is going to be testing one of our functions, and it has an interesting size list precondition. So what do you start out with? You're going to need some kind of generator. So most of these frameworks come either with a built-in generator, or you can use a macro annotation on your data type to produce a lot of random values of that data type. And then the next part of our step is to take that data and pass it into the user-provided precondition. So this is the precondition to the user's function under test. So if your data does not satisfy this precondition, you're going to have to generate some new data. And here is our precondition, which is lists of some bounded integers length. So then we have the user's function in our test, of course, which we've provided our input to. And then we will check the output of that function against a user-provided post condition. And if this ever returns false, then we know we found a bug. And otherwise, we iterate for some large finite number of steps to look for one, continue looking for one. The focus of this talk is going to be on this inner loop here. This is where we are doing work on generating data that is not satisfying the precondition, so we're not actually making any forward progress in testing the user's code. So there's a question of like, how well does this default generator do? So we have our default generator for lists, and we have our size list precondition. And we find that in this case, only about 50% of the lists that we generated are valid. And that sounds okay, but as you start to have more restrictive preconditions, you're going to start to reject a lot more inputs. So now the rest of this talk, we're going to use our motivating example of a precondition around even lists. And we find that this rejects 90% of the lists that are generated. So only about 10% of lists are actually valid. So one thing users can do is that they can go and write specialized generators. These are generators that they ensure only will produce data that is valid for their precondition. And of course, we find that these generators produce only valid data. One of the problems is that users actually have to go and write these specialized generators to actually ensure that they have the properties they're interested in. And additionally, if you have for every new test that has some different precondition, you're going to have to write some different generator. So, but still, like, we've taken our problem before and we've reduced the problem from who wants to write tests to who wants to write test input generators. And this is not just a meme. User studies have found that developers do not want to do this. They would much rather just use the derived generators whenever possible. Okay, so this looks like a good opportunity for program synthesis, actually. And let's look into that a little bit. So program synthesis requires a specification of some kind. So here, I'm going to start with just a high-level specification, which says that our even list generator should only produce non-empty lists containing the even integers. And then additionally, you're going to need some structure. So here, we're going to use a set of components and then an initial template to work off of. This is a very standard template for probability-based testing, because generally speaking, you want all your generators to be sized and to have finite number of steps for their recursion. But if you apply most of your traditional program synthesis techniques, what you might get is a very unsatisfying generator like this. This is a generator that no matter when you run it, will always produce a singleton list containing 0. But I would like to note that this generator does satisfy the initial preconditions we proposed, which is that it only produces non-empty lists of even integers. In contrast, a better specification would be one that says that our even list generator produces every possible non-empty list containing the even integers. And this is what we call as a good generator because it gets a sufficient set of the values you'd expect. So what is our missing ingredient here? Our missing ingredient is actually coverage. So when I've been talking about every here, I've been talking about some past work by my collaborators on coverage types. This is a coverage type specification up here. And what we're trying to define is these generators that can produce every possible value that our users might be interested in. So formally, before when I was saying, like I was using words like only and every, only corresponded to our, like a traditional safety property, and every corresponds to a coverage property. To give you a little bit of intuition for how these coverage types work, if we imagine our generator as producing a set of outputs, then our safety properties are over-proximate. So they set an upper bound on the set of all values that can be produced, but they don't necessarily tell you where inside of this larger set are the values that you're actually producing. In contrast, coverage is an under-approximate property. So in this case, it sets a lower bound on the set of values that can be produced. And then you could potentially go over, but it necessitates that you must produce at least this set of values. So the rest of this talk, I'm going to be presenting my work on COB. COB is combining work on coverage type verification, which are these coverage types, and taking some ideas from the type-based synthesis world according to safety, and bringing these together in quite a nice form for product-based testing. Okay, so how does COB work? COB, in a nutshell, is two phases. The first phase is going to be identifying the set of missing coverage from our either incomplete generator or from the initial template we get. So we identify the set of missing coverage that we can abduce, and then we're going to take that missing coverage and we're going to localize it to a series of typed holes to create a typed sketch. From that, we can then proceed to do an enumeration where we will enumerate sets of terms until we can find terms that satisfy each of our holes, and we can use them to repair our sketch until we get a complete generator. So I don't have enough time to talk too much in detail about our first phase, but I'm just going to walk you through our motivating example. So the input to our first phase is, of course, our coverage type specification as we have before, and we have our incomplete generator. And through our two different steps, we will arrive at this typed sketch. So this is a sketch with a series of typed holes in it. Each of our typed holes has a corresponding typing context, and we've pushed in all of our missing coverage that we're going to be looking for. Okay, so given our typed sketch with these typed holes and our coverage type specification, we can now proceed with the synthesis process. Okay, so synthesis, we're going to be applying a bottom-up cost-based enumeration. And our goal here is to continue iterating until we can exhaust the space and find the set of repairs, or you hit some upper bound, or you hit some timeout. So our first step is to choose one of the holes. And remember, one of these holes, they come with a corresponding typing context, a set of local variables, which is going along the path to that hole, and then the missing coverage that we're looking for. And I mentioned that we're doing bottom-up, so we're going to start from a series of variables and constants, and we're going to start combining them together with our components. And this is how we're going to proceed with our enumeration. Each of these terms is going to be, we're going to run type inference on each of these terms with relation to the corresponding typing context of that hole. We're going to use this to infer a coverage type for each of them. And then we can perform type checking and checking for equivalence. So we can look at the coverage type of the type we just inferred. We can compare it to other similar coverage types to see that we actually have a unique set of coverage for each of our terms. And we can throw out ones that are not unique. Okay, and then so for each of these terms, we can also keep checking them against the missing coverage that we're looking for in our typed hole. And this is just a subtyping check. So we can do a nice little subtyping relation. And for our initial set of terms, these do not help us with our missing coverage, but that's okay. We'll hold on to them, and we will use them to help enumerate some larger terms. So as we go, we're going to start to create some more complex terms. Especially, we like to prioritize recursion, because it often will create shapes of coverage that are well aligned with what we're looking for. So here's a couple examples of some terms you might start to enumerate. And as we go, this is where we will start to prune out some terms. So one of our terms we're going to prune out for safety reasons. So if you recall, make a recursive call with intgen, that is any possible integer. This violates our structurally decreasing recursion property, which would be very bad. Your generator would never terminate. So we will prune this out as being unsafe. And likewise, if you, in this case, we call evenless generator with 0. So that would just be equivalent to our base case, which is a term you might have already enumerated by now. So this would be equivalent to a coverage to that this other term. So we can prune that one out as well. So we can keep going. We can start to enumerate even larger and more complex terms. We can run type inference. We'll check. We'll do the normal type checking and equivalence check, the uniqueness checking. And in this case, when we compare the inferred types of these terms with our missing coverage, we find that our subtyping check succeeds. That means that these terms could potentially be useful in repairing of the holes. So we'll proceed to that now. So how do we actually do the repair? So as we've been inferring the types for each of these terms, we've been building a subtyping lattice. This is a lattice where our partial order is on the subtyping relation, and we've been putting useful terms into this lattice. So here's an example of what this might look at this point. Then what we're going to do is we're going to insert our typed hole into the subtyping lattice. And this leads to one of two things. Either we immediately find a term that is equivalent to our typed hole, in which case, great, we're done. Otherwise, we can perform a lattice join. So we can look at amongst the children of our typed hole, and we can see if the coverage of all the children of this typed hole is sufficient to cover the full set of missing coverage. In that case, we know we're going to have a solution, and we can prune out any unnecessary terms and get a nice repair. Otherwise, you'd keep going. Okay, that was cool and all, but let's talk about some numbers. So I've implemented COB in OCaml. It's about 4,500 lines. I want to have COB be able to reason about a variety of different data types, so lists, trees, redback trees, and the lambda calculus. Additionally, we want to be able to use a variety of different properties, so different kinds of size lists and trees, different kind of data constraints, so sortedness, uniqueness, and duplicates, variety of different validity constraints around BSTs and redback trees, and then of course well-typedness for the simplicity type lambda calculus. And then for each of the kind of holes that we want to repair, we want to have a variety of different branch conditions and local variables. So what I've done is I've gone into the literature for a variety of the different generators, and I've taken them and I've made them incomplete by removing different terms from them. And in our most general case, this would be like, in our initial example, we had that very loose template that we use for even list. This would be our most general form, where there's only a little bit of control flow, and then there's no actual coverage being provided from the template. So one of our results is that COB is actually pretty fast. So when we look at our most emptiest template, we find that COB in general finds the most precise coverage in about under a minute for a variety of our different benchmarks. And additionally, when we try and compare COB against other forms of repair strategies, because as I mentioned, COB is taking into account both coverage and safety, we might want to ask, what if you just did one or the other, right? So for here I'm talking about the coverage only repair. So if you only wanted to repair for just getting a good set of outputs, you could use the default generator. So in this case, the default list generator. That would always be a valid repair. So this would help you get a coverage complete generator. However, now your generator is going to start to produce a lot of invalid terms. And we characterize this by running all the different the COB generator and all the different variations for 20,000 outputs. And we track how many of the 20,000 are actually valid. And as you can see, in the worst case, in your sketch variation, only about 2,000 are valid, so about 10%. So there's a whole bunch of other stuff in the paper, which I'm not going to be able to talk about. We, of course, evaluate on the simplicity type lambda calculus. We have a whole bunch of more numbers and analyses that you can see. We compare against the safety repair strategy. We looked at dynamic constraint solving. So if you had a constraint solver at runtime trying to find valid and unique terms, this is rather slow. We also look at how COB performs when on perturbations of the components, and we have a soundness theorem. So in conclusion, users don't want to write input generators, and our solution is this coverage type guide to repair. We have an initial phase where we find the missing coverage, and we have a second phase where we actually do the repair, and we synthesize in terms. And COB is an efficient one-time synthesis process for this task. Thank you. I'm happy to take any questions.
We have time for a question or two.
Or you can find me on lunch.
Hello, as you mentioned, thank you for the great talk. As you mentioned, the lambda calculus as a simply type lambda calculus as your example. How do you deal with the mutually dependent specification? Like in case of lambda calculus, there is normal form and neutral form. If you want to generate the normal form only, then you need to depend on normal form and neutral form to generate that kind of specification. So I'm wondering, how do you actually deal with the mutual recursion in case of there is a mutually recursive specification for the generated input, generated output, generated test cases?
So the simply type lambda calculus generator that we use is from some past work. So I believe this generator is probably a little bit simpler. So it doesn't have this, we don't have to synthesize two functions at the same time. So in our case, we do have a bunch of recursion, but it's not like flipping back and forth. So maybe that would be a more complex generator we could look into. It's kind of interesting to think about how you do multiple synthesis tasks at the same time.
Thank you for the answer.
Take the last question over lunch, just out of fairness. Thanks very much, Patrick.
Yep.
Enjoy lunch.
for us to start with memory and memory models.
Thank you. So I'd like to start the talk by introducing Jillian, which is a tool that my colleagues of mine have made in the past. And it's what they call a parametric compositional symbolic execution framework. It's a bit of a mouthful, but it's basically a symbolic execution tool with a number of features. For starters, it's parametric on the memory semantics of the language you want to analyze. So if you want to analyze C programs, then all you need to do is provide a C memory model to Jillian, and now you have a tool that can analyze C programs. And you can do the same thing for other languages like JavaScript. So just provide a JavaScript memory semantics to Jillian, and now you have a tool that can analyze JavaScript programs. It's also compositional in the sense that rather than, yep, that's right. Okay, right, yeah. Sorry. Hello? Is it, all right, yep, right, cool. Yeah, so it's compositional in the sense that rather than analyzing the program as a whole, you analyze the program by its parts, and specifically it's about functional compositionality. So we analyze function by function, and we acquire the specifications of the function and use these specifications when we encounter a function call in the future. So it makes analysis a bit more scalable. And finally, there's another feature that's absent in other similar tools like Vibe or Verifast, and it's the ability to do not only separation logic-based specification verification in an over-approximate style, but also incorrectness separation logic-based automatic specification synthesis through biabduction, which is an under-approximate analysis. So Jillian's pretty versatile, and it has been successful in terms of analyzing real-world code in the past. So it's been used to analyze some C and JavaScript libraries through symbolic testing. And through separation logic-based verification, it's also been used to verify AWS code and some standard library code in Rust. So it's pretty great. But at some point, we stopped and took a step back and started asking a question. Why does it actually work? How do we know the tool is actually sound? Or better yet, what does soundness mean in the context of Jillian, or even any symbolic execution tool, compositional symbolic execution tool? So to address this, there were some attempts to provide a formal foundation for compositional symbolic execution tools in the past. But there's a number of problems with these works. So for starters, these works are tailored specifically towards Jillian. So it's not really interoperable or compatible with other frameworks like Verifast or Viper. And the formal foundation only covered over-approximate based analysis and not under-approximate based analysis, right? Also, the memory model instances were not proven to be sound. So when it comes to like the C memory model or the JavaScript memory model used in the previous works, we just had to trust that the implementation was done correctly by the devs. And finally, it's not mechanized, so you had to kind of trust that the pen and paper formalization was correct. And so this is where our work comes into play. We introduce our what we call the CSE theory, right? So it has the following features. So it's parametric on the memory model, just like Jillian. But now we have a memory model theory, so we have properties on top of the memory model. We also have a general foundation, formal, compositional symbolic execution foundation for not only separation logic-based analysis, but also incorrectness separation logic-based analysis. And to show that we have a sensible, theory, we instantiated a number of various memory models. So it kind of ranges from something very simplistic like the linear memory model to something a bit more substantial like a capability hardware enhanced model. And finally, it's mechanized in ROC. So you don't have to trust that our theory is correct. It's certified by a theorem prover. So for today's talk,
I'm just going to briefly touch some key aspects of our CSE theory, and in particular, I'm just going to introduce the engine and introduce how how we would formulate and attempt to prove the soundness property. I'll also show how we would instantiate a linear memory model during this process, and if we have the time, I'll briefly talk about some of the other instantiations. So let's start with the theory. As I said, the main component is the CSE engine. And if you kind of zoom in, we have the symbolic semantics, which is pretty standard of symbolic execution. And because we're dealing with functional compositionality, we need a way to use function specifications during function calls. So we have an assertion language, and we have the symbolic semantics depend on the assertion language. And finally, to ensure that we have a soundness theorem stated, we have the concrete semantics. And really, the idea is that we link between the symbolic semantics and the concrete semantics. Right? So that's the overview of the CSE engine. And to deal with memory-specific stuff like memory actions and spatial resource assertions, this is where the memory model theory comes into play. So if we zoom into the memory model theory, we realize we have a structure that's pretty symmetric to that of the CSE engine, right? So if we kind of look at it from bottom top, we start from the concrete memory model. So here we define the data structures, semantics, and properties of the concrete memory. Just to give an example of instantiation, if we consider the linear concrete memory model, the structure of this would just simply be a mapping from locations to bytes, location to values, right? The next level is the resource model. So here we actually define the spatial resources of the memory. So it's just defined by this resource predicate, and we define what it means for this resource predicate to be a model with respect to the concrete memory. And for the linear memory model, the way we define the resource assertion for this would just be a standard points to predicate. And we also provide a way to relate this to the concrete memory by saying we have a concrete memory with exactly one mapping from ins to outs. And then finally, we have the symbolic memory model. So it comprises the data structure and the semantics, but it also provides a way to remove or add resource assertions from and to the symbolic memory, right? So for the linear memory model, the memory structure is just a symbolic lifting of the concrete counterpart. And for the two operations that remove and consume and produce, it's about either removing a cell assertion from the symbolic memory, or it's adding a cell assertion back to the symbolic memory. All right, and then finally, to make sense of these operations, we need to have some kind of soundness theorem, soundness statements. So here we actually state what it means for these operations to be sound. And the instantiation is about actually proving the soundness of these operations. So here's the important part. So we have the soundness statement of the memory model, and we're going to use this to prove the soundness statements in the CSE engine, right? So that's the idea. So now, how do we define and attempt to prove the soundness theorem in the CSE engine, right? The basic idea is that if we assume we have a symbolic step, right, and the final symbolic and concrete states are related by somehow, then there exists an initial concrete state such that there's a corresponding concrete step, and the initial states are related, right? So in other words, it's essentially saying that we have a symbolic semantics that under-approximates the behavior of the concrete semantics. So usually we now have the soundness theorem, and if we want, so we would usually do structural induction over the symbolic semantics, and perhaps the most interesting case to consider is the function call case, right, which is kind of what the standard CSE tools like Gillian, Viper, and Verifast would do. So first, it's important to understand how the function call works in the symbolic semantics. So let's assume we're trying to call a function, and we're in the symbolic state sigma. And let's also assume we have the specification of the function, right? The idea is we want to match part of the symbolic state that corresponds to the precondition in the function specification. Once we've, and this operation is, the matching process is done through this consume operation, right? So once we find a match, which is this sigma p over there, we're going to remove it, and then we're going to generate a new symbolic state that corresponds to the postcondition of the function, and then we're going to add that back to the final state. So that's essentially the idea behind the functional call semantics. And so here, these consume and produce operations, we didn't set a specific implementation. Rather, we made it parametric, since there's already prior work that allows us to define the properties of these consume and produce operations. So here it's saying, we have these two operations, and we can define the properties through some soundness statements, and we can use this to prove the function call case for the soundness theorem. But there's a problem with this work, because what happens if we have spatial resources in the specification, right? It's a big problem because this work is not parametric on the memory and spatial resources, so it's fixed on the linear memory, and so we need to find a way to generalize this work a little bit more. But if you take a step back and go to the memory model theory that we had before, that I introduced before, we realize that we have these consume and produce resource operations. So this is specifically for spatial resources. And we also have behaviors that, we also have properties that state the behaviors of these operations, right? So going back here, the way to tackle this issue is to use the specific consume and produce resource operations. And in terms of proving soundness, we can still use the consume and produce algebraic interface that that was done before, but we extend this work to support the consumption and production of resource assertions. So there's many more interesting cases to consider, but more of the details of those cases are in the paper. So yeah, that's the overview theory, and I just want to briefly touch on the some of the instantiations that we had, right? So I've already kind of described about the linear memory model instantiation, but for the other ones, we also proven some more interesting ones, and we've proven them to be OX and UX sound. But perhaps it's worth pointing out that there's a more substantial one called the cherry memory model. For this one, we proved it to be OX sound, but we're still working on the proof behind the UX soundness. But you can see, even just proving for the OX case, it takes about 19,000 lines of code, which is a big effort. But really, the point is to show that our CSC theory is capable of instantiating more serious memory models. So to conclude the talk, we have this general mechanized parametric compositional symbolic execution framework. In the future, it'd be nice if we could kind of have some kind of library that eases the instantiation effort of these memory models. So currently, we just kind of have to build everything from scratch, and it takes a lot of time to kind of get everything to work. And eventually, it'll also be nice if we could instantiate other memory models that's already in Jillian. So there's more details in the paper, and if you're interested in the actual formalization, it's also available online. So that's the end of my talk. I'll be happy to answer any questions. Thank you.
Not any question, just one.
All right, cool. Yeah.
Thank you for the talk. Microphone's turned up too loud. The symbolic execution engine is parametric on the memory model, but it looks like for the soundness result, you're relying on the symbolic memory model that you created, the operations that you defined from the symbolic memory model. So the soundness proof still relies you to have picked an instantiation already. You don't have a parametric soundness proof.
So with the memory model, you still have to define the memory semantics and the actions and the properties, and then you have to define the soundness over these over those semantics. But once you have that, then you can use that to prove the general soundness term in the CSE engine. Yes.
Okay.
Okay, so you have the floor. Sorry, we have to be so fast.
Okay, so first a caveat. Thomas Bagrel has thought about all of this much more than I did. So everything smart is his, everything dumb is mine. With that in mind, I want to talk about map. Takes a while, okay, it's fine. So map famously, the map on list, if you write it the natural way, is not tail recursive, and this is kind of bad. It's kind of bad because it consumes stack space, and this is limited and all that. And the usual solutions are something like the two functions on the right. I don't think you can read it very well. I chose my colors poorly. They look brilliant on my screen. I'm really sorry. So it's all fairly systematic. One way is to transform map by continuation. You take a continuation, everything becomes tail recursive. That's nice. Though you might notice the question mark at the bottom of the slides. It's not really a good sign usually. And another solution is to accumulate everything in reverse and reverse the list at the end, which is not really a different solution. It's just a defunctionalized version of the first one. It has the advantage of eliminating that all three functions do exactly the same thing. You switch stack space for heap space, but at the end of the day, this just means we go down the list and then we go up the list. This is a two-pass algorithm, and that's why it's kind of bad. And the real problem with that is that it shouldn't be, right? If we allow mutation, it's very easy to make a map that is tail recursive. You just keep a pair of a reference to the head of the list and a reference to the back of the list, and when you want to add an element to the list, you grow the back of the list by mutation. Here I wrote it in OCaml, so I had to change the type, but that's the way like a Java program would do it, right? But in a functional programming language, and at least a pure functional programming language, you won't be able to do that. You can't do that purely. This is mutation, and I'm jealous. And jealousy is good. Jealousy is, people do better things than me. Well, I can try to solve that problem. So that's where we're going. Also, it seems that, okay, my screen is broken, but it's fine. Okay, so one solution that exists today in OCaml, there's all OCaml code so far, by the way, but if you are into Haskell, there's a few Haskell slides at the end, is to add this tail modulo const annotation on map, and the compiler magically compiles it to the Java version, kind of. Just imagine it does. And that's really, really nice, because I don't have to do anything. You write the map that you want to write, no problem, and it is efficient. But it's not very flexible, right? You need to fall into one of these patterns that the compiler recognizes. And that's quite a few, but there's plenty of more things you can do if you have actual programming tool. So to solve this particular conundrum, I want to go a little bit more back in time, actually, and talk about an observation that Minamide did. I didn't write the date on the slide, so I don't remember when it was, but in the 90s. And the observation was, in the continuation passing version of map, you use the continuation in a very specific way.
For one thing, the continuation is used linearly. And then there's another observation that it is used, I should probably just point it out directly, that it doesn't actually pattern match on L prime. You can read L prime? Yeah, you can. Okay, great. And with these two restrictions, it is possible to come up with a new type of functions. Here I wrote it linear arrow hat. So it's a restricted type of function that you will only use linearly because you're going to mutate it, so you don't want it to be, the mutation to be observable. And that never pattern match or does anything dangerous to with its argument, because otherwise you would read unrestricted memory. But with these conditions in mind, Minamide could take this function type or something that looks a lot like this and compile it to the Java version. That's great. So I guess this is the end of the story, but not really. There's much more things that we can do if you give us a little bit more fun. I forgot to mention in the previous slide that linear types are not necessarily necessary. Like Lorenzen and Lyon, who are specialists of saying linear types are not necessary, show how to do that with just reference counting and copy on write. That's more recent. So consider this problem. So I have a tree on the left. It's the tree of unit, so it doesn't matter what's in the nodes, but I'm going to label each node with its position in the breadth first traversal. So the root is 1, and then the two children of the root are 2, and then you have there are 3 children, are 4, 5, and 6. Do you know how to do that in pure functional programming? It's not like it's not easy. Like papers have been written about it, so it's not immediate how to write this algorithm purely. But on the topic of being jealous, you learn how to do that in imperative programming in your first year of algorithmic class. All of us know how to do that. You put references in a queue and you generate a tree in breadth first. It's very easy. So, yeah, I'm jealous again. So, the solution for that is to have some kind of restricted form of references. And the inspiration, again, is linear logic. In linear logic, the function is decomposed into a par and a primitive, like a first-class input type, that alpha dual. It's an input of type alpha. And we want similarly to decompose Minamide's function into this quickly symbol that we call an ampar and a destination, which is a first-class whole. So before that, we had only context. We had a list with a whole. Now we have a value for a whole. And that gives us a lot. And so, yeah, it's the same decomposition. And that gives us a lot. And the truth is that we can actually do a breadth first traversal with a normal algorithm. Like you have a queue, you put things in a queue, the queue is functional, but we know how to make functional queues, like you take dual lists or something like that. In the paper, we even use destinations to make the queue, so it's a lot more fun. But that's a discussion for another day. The point is, now it's really easy. Like if I give you the tool, I give you the API, you'll find how to do that in 15 minutes. And you have like, you have similar restriction on this ampar type than you had on the hat function, right? You can't read the output, the inputs in an unrestricted fashion. But then, like, this is really very easy to set up. But not everything is easy to set up. And the point is, linear types don't matter. Don't matter. Of course they matter. They don't suffice. Linear types don't suffice because destinations can break the linear contract. If I take a linear function like that, that is a function, a non-linear function, it just uses its argument alpha of type alpha only once. But it captures a destination. And during this function, I fill the destination with the argument, and the argument will escape. And the contract of linear functions that when I evaluate the result, I also evaluate the argument. That's a pretty lazy version to think about it, but the same story happens, right? The argument escapes instead of being part of the beta. And that is bad. That breaks basically every linear API out there. This is what you rely on, you break it. And in particular, that would break destination. If I can put a destination in a destination in an unrestricted fashion, then I can read uninitialized memory. So the solution that we had to come up with was a new type system. So it's an extension of linear Haskell. Linear Haskell is basically the stuff on the left. It doesn't really look like a type system, but it really is secretly. Because linear Haskell is a type system in a tradition that was first proposed by Gika in, I think, 2014, where the whole type system is parameterized by a summiring of modes. And modes with linear Haskell are just, am I linear or not? And we have to add, in addition, like numbers that represent scope, that represent, am I capturing a destination that I shouldn't? And so let's just put restriction on what we put in destination to avoid linear values escaping their scope. So this is a bit related, very vaguely, to Rust's lifetimes. But so every time we enter one of these AMPA, we increment the scopes and we just count how old things are so that we can use them in the right order. And there's a whole bunch of restrictions on destination to make this work. Okay. And infinity is an age for things that are normal values and they don't care. So these are really ordered summiring. You have the order on the top. And the fact that you have two summirings, the product of summiring is a summiring, and the type system almost works by itself. So I'm going to stop here. Here are a few links. Follow our blog. You will find more on this in the coming weeks, hopefully. Slides. The QR code is a link to the slide. And questions.
So this time you can take as many questions as you want, almost. So if you have a question, please go to the mic.
Do you have a slide with the actual code of the breadth first search traversal? Because I have trouble picturing.
No, but it's in the paper. You can look it up.
Definitely read the paper.
I have some slides with code, but not this one. Sorry.
Okay. And so, have you considered implementing it in Haskell or Camel or something else?
So the problem is the age system is an active type system, so you have to somehow fit it in, and you don't really have that luxury in Camel or Haskell. So what you have to do instead is finding appropriate restrictions of the general type system that will work for Haskell. But there is an implementation where the restriction is, well, you can only put unrestricted nonlinear things in destinations. That solves the problem because you can't break linear things anymore. But it's very restrictive. It's useful for some use cases. And there's the Haskell implementation. There's a JEC proposal to implement the compact region API that way. But there's and to go further than that, there are thoughts. Thomas has thought about that and designed some APIs, but it's very prospective. It was never really followed up with a real implementation.
So you think that the future functional programming languages should have this system, the general system, right?
I hope so. I don't know. Maybe.
Okay, are we done with the questions? So let's ask the speaker again. Okay, wonderful. So profiling now, please.
Thank you. Can you hear me? Yeah. My talk is about an approach to actually approximate the accuracy of a profiler using machine code level slowdown. And I did this work with Stefan Mahr. Profilers. Profilers are tools that allow you to observe performance behavior. These can be characteristics of an execution. They may be such things as memory allocation, object allocation, or how much time did we spend in a method, such as something like that. There are many types of profilers, sampling or instrumentation-based, but we're only interested today in sampling-based profilers, which is where you periodically halt execution and you collect a sample, some information. This may be as simple as the program counter, and then you can look at the metadata and you can know what method you're in at that point of halting. There's a problem. If you actually run a program with a profile attached multiple times, you'll start to notice the profile will change. Sometimes a method may take less time, sometimes a method may take more time. An actual real example of this is we ran the Delta Blue benchmark 30 times with async profile attached, and we just overlaid all 30 runs on top of each other. The error bars there are just showing the range of measurements we got. All methods that are highlighted in red are methods where in at least one run they were the hottest method. They were the method that consumed the most amount of the runtime. If your goal of using a profiler is to try and identify what is the most important method, this is not a very clear picture to actually understand that. And when you want to do some manual optimization, it's not entirely clear which method here you should target first. Why do we see stuff like this? Well, there are multiple reasons. Non-determinism. Compiler decisions, garbage collection, and interrupts can all influence how a program is executed. On top of that, the tools like profilers suffer from the observer effect. Work done by us and others has found that profilers, samplers, and instrumentation can actually influence an execution of a program, and this can dramatically change the execution, giving you an unrealistic view of the program, an execution that would not normally happen if there was no tool attached. What do? So you need to test, if you want to test a profiler to see how accurate it is, you need some sort of stable ground truth that you can test against, some known performance behavior that you can be certain exists. A possible solution to this is slowdown. Slowdown is where we deliberately introduce measurable and controlled changes into the program to make the program run longer. Specifically, we're trying to make the methods run for a longer period of execution. We're not changing the logic or the semantics of the program, we're just establishing a new program behavior. It is an approximation of the program behavior. How do we actually slow down a program? Well, we're targeting at the basic block level. That is just a way to organize machine code where you have one entry point and one exit. This is terribly useful to target for slowdown because it means once a block is executed, our slowdown is guaranteed to be executed. We're targeting basic blocks almost at the very end of the compilation pipeline, so we're way after inlining and dead code and loop transformations, so we should have a minimal effect on compiler decisions. The type of slowdown we're using are wasteful MOVs. On the right, highlighted on line 3 and 5, you can see we've added these MOV which perform a movement from the same register to the same register. This should not change, this will not change the value in the register, but it will cause the CPU to waste some cycles in having to deal with these. To determine actually how much we add, how many of these wasteful mods we add, we're using hardware counter feedback. We're using vtune, which we progressively will add slowdown and use the vtune report to actually see how much slowdown we've caused, and that should give us a more accurate number of how much we're adding. The research questions we had in the paper were the following. Does slowdown at a block level result in accurately slowed down programs? So this is a test on whether or not we can actually achieve and a target slowdown. We chose 3 target slowdowns of 50%, 100%, and 150%. And we wanted to see how close can we actually get to that target slowdown. The next one was, do sampling-based profilers report the same percentage of runtime for identified methods? This is testing whether or not our approach has any side effects. Even though we're making the execution 100% or 150% longer, you would still expect the ratio of time spent to methods to be the same. The percentage of runtime for each method should still be the same, they're just X amount longer. And finally, do sampling-based profilers accurately detect changes to a slowdown method? This is actually the real test of, we can now evaluate profiler accuracy. We're going to deliberately make parts of the program run slower, and we can evaluate profilers on whether or not they can detect that slowdown and how accurately they detect that amount of slowdown. Our experimental setup, we're using Java, we're using the Graal compiler, which is a just-in-time compiler. Specifically, we're making use of compiler replay. This is a feature Graal has where for a given execution, you can get it to log what compiler decisions were made, and then you can refeed that into it for the next execution. What this should give us some level of stability in compiler decisions and should make our results a little bit more stable. We're using the 14 benchmarks from the Are We Fast Yet suite, deterministic, 5 macro, 9 micro. Each benchmark execution is 500 iterations, with each iteration being about 100 milliseconds each, and we will repeat that 10 times for each benchmark for each profiler. The 4 profilers we're using today is Async Profiler, Java Flight Recorder, JProfiler, and Orchid. So, for the first question, do we accurately achieve slowdown? So, for our 3 target slowdowns of 50%, 100%, and 150%, yes, pretty much. For 50% and 100%, our medium is bang on those targets areas, with only a variancy around 5 to 10% between each benchmark. For 150%, we've slightly underslowed with the medium, 146%, but that is well within, and we believe it is achievable to increase the slowdown. So underslowing is not the worst possible problem. Do sampling profiles report the same percentage of runtime? So this is a test on whether or not our approach has any side effects. Have we changed the performance behavior? When we pointed profilers at the program before slowdown and after slowdown, and we measured the percentage of runtime for each method. And we're plotting every method's percentage runtime. Now, if they have remained the same, they should be on the x equals y line, because it's the same ratio. For the majority of the benchmarks, this is true. It is, in fact, 13 out of our 14 benchmarks. The methods all remained within 5% of that line, which is definitely within noise variance. As you can see clearly, though, list benchmark, that backwards triangle, is off the line. It has the amount of time we spend in list has changed when we slow down. And this was true for all 4 profilers we tested. Why did we see this behavior specifically in lists? Well, we took a look at the amount of debugging information available in each basic block, Lear instruction for each benchmark, and list had one of the lowest amount of debugging information, 70%. We also specifically looked at some of the hottest blocks. List have those are the blocks with the highest amount of execution time, the blocks we spend the most amount of time, and we found a severe lack of debugging information. In fact, one of them which encompasses double digits of percentage of the runtime, had no debugging information. Specifically in JVM profilers like samplers, when they hit an instruction with no debugging information, it has to guess. It has to look at the nearest instruction, nearest debugging information, and use that for the association. And what this meant was when it hit our slowdown, it sort of exacerbated this problem. It meant that all of our slowdown had to be guessed in what debugging information it had. Do sampling profiles accurately detect changes in slowdown methods? So this, knowing now that our approach is accurate and it has minimal side effects, we can now test whether or not profilers accurately detect increase in runtime of the program. So we added 5 seconds of additional runtime to select target methods, specifically targeting individual basic blocks that solely belong to that method, and we added slowdown to those blocks, And on top of that, we added debugging information to our slowdown to guarantee that slowdown was correctly associated. And we tested whether or not profilers would now associate that additional runtime with the targeted method that has been slowed down. One of those tests is here. We made vector.hasSum 5 seconds slower, and we looked at if all 4 profilers would correctly identify whether or not this method has now got slower. Async and Java Flight Recorder, oh, and I must mention, because we knew the overhead and we knew the exact amount of slowdown we're adding into an accurate amount, we actually could predict the amount of additional change we would expect. So that actually gives us a degree of accuracy we can evaluate a profiler against. Async and Java Flight Recorder have identified correctly that vector.hasSum has increased in its runtime, and async's definitely within our prediction, and Java Flight Recorder is a little bit off, but it's definitely close to our prediction. JProfiler has not detected any increase in runtime in vector.hasSum, and instead has completely changed the result and has decided that vector for each is now slower, even though we didn't slow it down. And YourKit, most surprisingly, has actually detected a tiny change. It's now saying we spend a little bit less of the runtime in that method than we did before. So this is actually now, this is our practical way of actually evaluating profilers to a degree of accuracy. So, to conclude, measuring performance behavior is hard. You have to contend with the observer effect and non-determinism. Program slowdown enables us to approximate the ground truth. It gives us something measurable that we can look for in a profiler. Our approach to slowdown is accurate, and it maintains the program behavior, performance behavior. And approximating the ground truth enables us to detect inaccuracies in profilers. I'd like to thank JC Designs and the University of Kent and Stefan for this work. If you were interested, please have a look at the paper. That is the end.
So we do have time for some questions.
So you mentioned that the slowdown is being introduced after optimizations like inlining. So when you're trying to slow down a particular method, how do you make sure that you've hit every place maybe that it's being used?
We target every basic block in a program, every single basic block. Every single basic block gets an equal amount of overhead, so every block will be 100% overhead. We're not just targeting one place. We distribute the slowdown within the block, and what that means is when certain instructions in a block have different debugging informations, our slowdown should be hopefully close to whatever method that it was there. It's not perfect, but you can't know, with hardware counter sampling, you can't know to that degree of every instruction the correct amount. So the balance.
For the final thing though, you were like specifically slowing down vector.hasSum.
Yes, right? That one, we added debugging information to try and give the profiler the best chance of actually seeing it, because the sampler should hit that slowdown and it has the debugging information. So it's not guessing, it's just at that point, does the sampler correctly sample at that point and associate?
I see. So you guaranteed that anywhere that your slowdown was, a profiler should have associated that with vector.hasSum.
Yeah.
I see. Thank you.
Yeah.
Thanks for an interesting talk. How would your profiling approach cope with separately compiled code, say from JNI or something like that?
That is a very interesting question. I can't actually answer that at the right moment. I'll talk to you offline about that one specifically, sorry.
Maybe a last one?
Sure. Do you have any clue why the profilers sort of give these weird results, right? You clearly showed that there's something funny going on. Do you have any clue what?
There is a few reasons. Sampling skid is a good reason why they can be quite wobbly. The actual delay between when it actually halts and actually collects the sample, and there's a paper that I can't remember the name of it, but it proves that you can have very hot loops that can never be sampled because the skid always jumps over it. So there are cases where there is still a degree of sampling bias that exists, where some areas don't actually get sampled, and therefore they're biased to certain areas.
So in a sense, it's a bit of an incompressible problem.
Yeah.
Okay.
Yeah.
Okay, thank you. Okay, the floor is yours.
Okay, thank you very much. Hello everyone, my name is Junior Leff. I'm a PhD student at USI in Switzerland. And this is joint work done with Daniele Bonetta, Matteo Basso, and Walter Binder. And today we'll talk a bit about heap buffers. It's an efficient serialization library that actually can operate on data that is already stored in a binary format. So we will see what this is. So Google reports that 9.6% of all CPU cycles are spent just performing protobuf-related operation, including data serialization and deserialization. And this isn't unique to Google. Every large-scale system will have similar overhead. So to understand where this number comes from, actually we need to have a bit of a background. So every programming language has its own way of organizing objects in memory, right? So on the left, I show how objects are commonly organized. You have the language implementation that can choose whether it wants to embed metadata in the header or exactly what metadata goes there. Objects can move, GC can move objects around. But overall, all this scheme is optimized for large and sparse object graphs. Now on the right, I show a binary layout where we have a different representation. Now we have a dense, small representation. More importantly, it's platform independent, okay? So we don't have the problem of pointers that are specific only for one virtual memory address. And overall, this is optimized for I/O and message passing. So why is it a problem? Well, every time we need to send a message, we need to convert from in-memory to binary. Then we can push it through I/O. And on the other side, we need to reconstruct the object again. So this is actually an expensive operation, as I showed before. So it happens many times, billions of times per second across large-scale systems. And it's just an unavoidable cost we need to pay. It's often called a tax that we must pay just to convert our data, but in fact there is no useful computation happening here. So in this work, we challenge the need for this conversion. What if language VMs could bypass this cost serialization by operating directly on I/O-ready binary format? So this is the question we asked, and this is what we addressed with heap buffer. So before I show how our approach works, I want to quickly show some background, some related work on binary serialization in the JVM. So flat buffers is a prominent example for that, probably is the most popular one. It's a very efficient binary format. And in fact, our approach is binary compatible with flat buffers. However, there are two main problems that we identified. So the first one is performance, okay? So flat buffers is just a binary set of data. The VM cannot really see what is inside this binary data. It cannot see what objects are laid out. Because it cannot see it, it cannot optimize data access. As a consequence, accessing objects in such a way in flat buffers is more than 10 times lower than accessing standard Java objects. Secondly, less intuitive problem, but also a problem is limitations in the programming model. With flat buffers, developers, they must manually allocate objects in specific order, manually track offsets, and deal with immutable data. So overall, while flat buffers is a very efficient binary format, there is still a gap in terms of performance and programmability, and those are two things that we address with heap buffers. So as I mentioned, we are binary compatible with flat buffers, so we would inherit these problems, and actually we address this with our library. So what is heap buffers? So heap buffers design was guided by a simple vision. What if Java objects that are intended for data transfer, they could be already allocated in memory using a binary format? And this is exactly what we do. So let me highlight some of the key features. First, heap buffer objects, they are always allocated off heap directly using flat buffers binary format. What does it mean? It means that if we dump the memory of our runtime system, we have a valid flat buffers message that can be used in I/O. Likewise, if we receive a flat buffers message, we can also use the data right away without any deserialization. So we are able to bypass these operations. Secondly, we generate specialized code. I will talk a bit about this later, but actually we can generate code that is optimized for every message, and this means that we can trigger some compiler optimizations that will, where accessing heap buffer objects is almost as fast as accessing standard Java objects. Finally, we introduce a new programming model that can coexist with the existing Java programming model. And from the developer's point of view, it just feels like Java. We have automatic memory management, garbage collection support, and objects can be freely modified. So to understand how this works in practice, I will briefly introduce the workflow. We adopted the same workflow of flat buffers for compatibility reasons. And it all starts with a schema that describes the content of the message. So you have the objects, the relationships, and types. This is fed into the heap buffers code generator that will then generate specialized Java code specifically optimized for this message in particular. So the most important thing here is that since we know ahead of time what are the objects, what is their relationship, what is their types, we can actually generate very optimized code. So there are many things we generate in this code, but the two more important that I wanted to highlight are we generate a very efficient garbage collector. Okay, so every message has its own specific garbage collector that focusing on its own schema, and we also allow some tailored metadata that will be later used by GraalVM native image to optimize object access performance. Okay, so let's see the programming model. After we generate this Java file I just showed, we can include it in our application and start using heap buffer features. So before we see those, I want to introduce some concepts. Heap buffer objects, they are allocated in a special memory region that is called transferable heap. Okay, so this is separated and isolated from the main Java heap. Here, all objects that are allocated will be heap buffer objects. They will have flat buffers layout, and they will be managed by their own GC. To access this transferable heap, we can use this method open, where it simply accepts a lambda, and this lambda exposes the HP runtime to the user. So this is the only method where we actually have access. And what we want, our goal with this open, is to create a sort of dynamic scoping where it's clear for the user that he's actually modifying objects as are special objects, not regular Java objects. Okay? So let's see how we can create some objects using HP. So let's say we create some entities. They are directly allocated in the transferable heap. We can create an array. So far, E3 is a candidate to be garbage collected. And what we can see is that this looks just like regular Java objects, but under the hood, they are not. And actually, heap buffer objects, they have similar semantics as the upcoming Java value types from Project Valhalla. So we have more information about this in the paper. Let's continue our example. We can keep creating new objects. So this is the root of our message. We create a name and assign the array of entities. For the name, something special happens. This is a string. So for string is the only type in our system that actually it needs first to exist in a Java heap, and then we encode and copy it into the transferable heap. So there is an indirection here that later we will see in the experiments exactly what is the impact of this overhead. With our approach as well, we allow modifying objects. So let's say we didn't like the name. It's totally valid to set a new name. And finally, before we close this encoding, this scope, I want to show some broken code. So this is not valid. Okay, so this will not work. And the reason is that these two heaps, they are separate. So we don't allow heap buffer objects to reference Java objects, nor Java objects to reference heap buffer objects. So cross references are not allowed. We only allow only two mechanisms can do it. One of them I already showed, which is the HP message in purple. So it always points to the root of the message. And then we have an additional mechanism, which is HP ref, that can be used to hold a reference to a heap buffer object. So this has weak reference semantics. It doesn't prevent the garbage collector from reclaiming the object. So before using it in the next time, you need to check whether the reference is still valid. Okay. Now we close the message. We call prepare. And what happens is that we trigger a GC cycle that will reclaim all unused objects, and it will compact existing objects into a dense representation. So from this point onwards, we have a ready-to-use flat buffers message We can send it over the network, or we can continue using it in our application. We can call open as many times as needed, and we allow modifying and creating new objects. So then we implemented a prototype on GraalVM native image, and we conducted many experiments to evaluate whether this approach actually works. In this presentation, we'll focus only on end-to-end performance evaluation microservices, but in the paper, we have more experiments. So in this experiment, what we can see is that the outcome is highly positive. In 9 out of 12 applications, actually, we outperform the best serialization library in Java. And in the 3 cases, we achieve similar throughput, but still better latency. Now, zooming in the best case scenario, so what we are comparing here, measuring here actually is throughput and P95 latency. In the X scale, we have different message sizes. And we compare against Apache Fury, which is, so preceding experiment, we compared against many existing libraries in Java, and Apache Fury was by far the best, so it's our baseline. And we also compare against flat buffers since we are binary compatible with. For throughput, higher is better, latency lower is better. So overall, we can see that buffers outperforms in all message scaling sizes by many times, so 2.4 times for throughput and 4 times for latency. Finally, we also need to show the worst case performance. So this is the only case in all applications where we lose a bit to Fury. And the main reason is what I explained before. So this schema uses a lot of strings. So they add some memory pressure in our system because we need to allocate 2 times. And even so, we achieve actually a great performance. So we are comparable in most scales, but up to 8% lower throughput, and still we achieve better latency. So to conclude, I presented heap buffers, an efficient serialization library that can actually bypass serialization and deserialization, and this is done because objects, they are already allocated using an IO-ready binary format. So we demonstrated how we can use specialized code generation to optimize both performance, improve performance, and also improve flexibility in the programming model. And experiments have revealed that heap buffers can outperform existing serialization libraries in Java. So you can find more implementation details in the paper. I don't have time to cover all of them. And all our source codes are available in the artifact, including the modified GraalVM native image compiler. So thank you very much, and I'm happy to take your questions.
So we have time for a couple of questions. You will be the one this time.
Thanks, this is really interesting. The thing I've seen that's a bit like this, but I'm not sure it's that similar, is Kaplan Proto, right? Because the idea of Kaplan Proto is you have an in-memory representation that you can work with directly, so you do a computation on that, and you never have to re-encode to do your I/O. So is it a similar approach, would you say? Or?
Yeah, so actually, Kaplan Proto is, I would put it on the same level as flat buffers. So right now we chose flat buffers, but actually we could have used Kaplan Proto binary format for our approach. So our approach is built on top of this binary format.
Okay, cool. I'll read the paper, thanks.
Yes. Sorry.
So maybe an answer to your title is debugging, right? Because the problem is debuggers rely on sort of a fixed layout in memory, and if you destroy that, then the debugger doesn't know anymore. Have you tried instrumenting a debugger with a sort of like a hook to allow it to read these serialized things to see whether you manage to get sort of the good experience with also the efficient format?
So actually we didn't try it, but it's a good idea. No, so far we didn't try to use a debugger in this. Thank you.
Hello. One question is that these heaps are garbage collected, or you fence the garbage collector from going inside and traverse these objects?
So, okay, so for this question first, thank you for asking. It's, we completely have a separate heap, so the regular GC doesn't touch our data.
And
we have our own garbage collector.
This heap is in memory or is on a storage device?
No, it's on memory.
It's on memory.
Yeah. Of heap, but on memory, yes, on the main memory.
Okay, and continue my question is that, okay, you have this object there, so one opportunity is to avoid to fence the garbage collector from going and scan these, because I think these they have the same lifetime. So when you perform heap deallocation, you can reclaim them together.
Yes.
Yeah.
Yeah. So actually, this was one of the ideas we had. Since these objects they have different semantics as regular Java objects, we can kind of specialize them. And for that, we implemented a very simple garbage collector. It's not as fancy as G1 or any of them, but it does a very good job. So we have measured the GC, the overhead of our GC, and it's really small.
Okay.
So we already took this into consideration.
Okay.
Yeah, later.
Thank you. Fine. Thank you so much. So, please.
Okay. Hello everyone, I'm Fei Chen. I will present ImTim, automatically converting in-memory image representations using a knowledge graph approach. Okay, in many domains, data across libraries may represent the same abstract concept, but it's stored in diverse in-memory representations. So when combining functions from different sources in a single program, this difference forces users to deal with the conversion details. Managing these low-level technical details distracted them from high-level tasks. So our research addressed this challenge, focusing on image processing as a concrete example domain. So for example, imagine we want to use two functions together. The function on the left side produces the output here, and the function on the right side expect an input. So at an abstract level, both of them represent the same thing, image. But in practice, you see their in-memory representation differs. One may produce a PyTorch tensor in a float format, which value in the range 0 to 1 using RGB channels in a channel-first batch style layout on the GPU. So in contrast, OpenCV functions typically extract the NumPy array in on-site integer 8 format with values in a different range, use BGR channels in a channel last layout on the CPU. So bridge this mismatch requires manually to handle conversion steps to keep capability, including device transfer and channel reordering, data types, and so on. So this low-level implementation, for example, here in the dashed box, distract the user from the high-level image processing operations. So a common approach is through using intermediate representation approach. This method standardized data exchange by converting all formats to and from a fixed intermediate format. However, this typical approach has two limitations. First, runtime overhead. Every operation involves repeated conversions, such as going from IR to operation and then back. Second, it introduces development effort. For each operation, developers must write and maintain conversion code to and from the intermediate representation. So we introduced ImTim. It's automatic to convert in-memory image representations using a knowledge graph approach. So at the core of our method is a graph. So we introduced this novel metadata structure with the key features that uniformly describe in-memory image data across different libraries. Each metadata will form a unique node in the graph. And the edges between nodes represent valid conversions and are annotated with code templates that perform the actual conversions code across several libraries. So the graph was constructed to capture this metadata instance and their associated conversion codes across several libraries and frameworks. So to design the cost of a conversion edge, we benchmarked the execution time of each a conversion across image size on different multiple image resolutions. The results showed the execution time was negligible to at all resolutions. So we do not include the execution cost as a factor in the edge cost within our graph model. However, some conversions like adjusting bench size or reordering channels preserve precision. Others like converting from float 32 to integer 8 or from RGB to green scale introduce the information loss. So to capture this difference, we define an information loss flag. It's set to 1 if information loss occurs and 0 otherwise. Some conversions may modify 1 or more attributes at a time. So we computed a conversion constraint score, which counts the difference of immutable attributes by the conversion edge, plus a penalty if this conversion process crosses the CPU and the GPU boundaries. So the total cost of edge is just a tuple with these 2 elements. This cost is evaluated lexicographically, which means we prioritize preserving information and only then try to minimize conversion effort. Okay, so in between, just follow 3 steps: just search, synthesis, execution to perform the source image to the target image needed for this operation at the runtime. So for graph search, so first in between, just retrieve the source metadata from the given image. Then, because many in Python or other language, many functions can accept multiple image formats. So system will identify the closed matching metadata for the target operation based on the preset. Okay, with both the source and the target metadata identified, we just use A* search to find the lowest cost conversion path between the source and the target metadata nodes. Okay, along this lowest cost path, the conversion code from each edge were collected and then assembled to executable Python snippet. This Python snippet can be just executed to convert source image to the target format. So that's all for our method. Pretty simple. Just A* search and then code synthesis, code string synthesis, and execute. Okay, so the first question is, can ImTeam guarantee a least cost path between image formats? Okay, let's first look at our heuristic functions. We use a very simple and safe heuristic. It just calls how many metadata attributes differ between the current node and the goal node. This captures how much transformation effort is still needed. So a heuristic function is defined as admissible if it never overestimates the true cost to reach the goal from the node n. So our heuristic function satisfies this property. So A* search, when guided by admissible heuristic, it's guaranteed to find an optimal path from the start node to the goal node. So okay, next question is, can it used in practice? So we compared the 2 approach, im-to-im and a baseline, which corresponding to a manually writing conversion code. It only executes pre-compiled conversion snips. So there was no existing benchmark for this task. So we just performed the brute force evaluation. For every possible conversion between all spotted image types, we generated random images of various sizes, then measure the execution time when using both methods. We found the relative overhead of im-to-im decreased with increasing resolution due to a monetized of graph search and synthesis. This is because the cost of the graph search and the synthesis This is because the cost of graph search and the code synthesis get amortized compared to the larger workload of the converting high resolution images. So im2im introduces the negligible overhead, which means it doesn't impact practical usability, even with the realistically sized images. Okay, so next question is what can we do with im2im? Firstly, im2im can be directly used in textual programming activities. Developer can write code in Python, for example, can freely connect functions from different libraries without worrying about conventional details. Secondly, it enables user to reuse functions across diverse formats. For instance, a visual debugger for neural networks can work with images, no matter it comes from PyTorch or TensorFlow. Most importantly, it can be used to enhance visual programming systems. So visual programming systems are environments where programs are built by connecting these visual nodes. Each node represents operation graphically. As you can see, this is a very simple blockly example. So more practical application used to enhance visual programming systems. So let's consider visual programming that supports build image processing tasks. For example, this task involves denoising, also detection, and optical disk annotation. So in the basic blockly just the base visual program system, as you see, these functions used are from 3 libraries: OpenCV, SciImage, and Pillow. The steps in the dashed box are the necessary conversions to issue capability in terms of data types, color channel, pixel intensity range across different image formats. So in the blockly based visual programming systems enhanced by im2im, all the conversion steps are automated, enabling no programmers to focus only on high-level image processing. For example, here, only read image, like denoise, filter, and annotation. So similarly, this is another example involves denoising, super resolution, and contrast enhancement. Again, in the basic blockly based visual programming systems, we use functions mainly from 2 libraries, SciImage and PyTorch. And the functions in the dashed box are the necessary conversions to issue capabilities in terms of data type, pixel intensities, mini-batch style, memory layout. So again, in this using im2im, all conversion steps are automated. So to summarize, im2im automatically converts in memory image representations across multiple libraries using a knowledge graph. So it's guaranteeing the least cost conversions, will minimize information loss, and it can be used in practice, especially to enhance visual programming environments. So beyond the images, this approach can be extended to geometry entities, which difference in data types, coordinate systems, units, and other attributes. And also it can be extended to audio formats and other domains. Thank you for your attention. I'm happy to take questions and comments.
So we do have time for 1 or 2 questions. So maybe a quick one. I'm not sure I have really understood the experiment you have been conducted. Could you give us some details about the implementation and what you are comparing to what? When you compare with the baseline, at some point you mentioned something, but
yes, you mean
you have been quick on that.
Yeah. So you say that our im2im just follow this pipeline, and the baseline is just simulate how people to manually write the conversion steps, and it's only execute this pre-compiled conversion code. We want to see if this graph search and synthesis, these 2 steps, to see if have larger influence or not.
Okay. Okay. Good.
Thanks.
Thank you. So let's take the speaker again.
Okay. Hey everyone, my name is Reese Levine, and on behalf of my co-authors, I'm here to present our paper, Safe Race, Assessing and Addressing Web GPU Memory Safety in the Presence of Data Races. So let's first start off with some highlights from this paper. So what we did is we identified what we call a specification vulnerability in Web GPU. And what I mean by that is that Web GPU tries to maintain some high-level safety properties, but its specification actually, when you read it closely, is not strong enough to prevent valid implementations from violating these safety properties. And specifically in our case, that's memory safety. So even though a current implementation may not expose this vulnerability, it's possible that it could in the future. So that's why we call this a ticking time bomb in Web GPU. So we performed several threat assessments to determine the susceptibility of different GPU frameworks to this vulnerability. And we found in the low level that there were actually valid memory safety vulnerabilities in GPUs from AMD and Apple that we reported to the vendors, and we got a CVE from AMD, for example. And we also found potential issues in a pre-release version of the Firefox web browser that we reported to Firefox and was fixed by them. To fix this vulnerability in the Web GPU specification, we introduced and formalized what we call the Safe Race Memory Safety Guarantee, or SMSG. And we evaluated the performance of our fixes, like how much it affected performance of programs on 10 important benchmarks, and we evaluated the adoptability of our proposals on 21 different compilation stacks for 81 hours using fuzzing on various browsers like Chrome, Firefox, and Safari, and Edge. I don't have time in this talk to go over all the details of our work, so I'm going to specifically focus on what the specification vulnerability is in Web GPU and how we fix it. Before I get into the details, I think there are a few high-level insights that I hope people kind of take away from this work. The first is that accelerator support in security-critical environments comes with new opportunities and also challenges. For example, Web GPU is an interface that's exposed by browsers to users to write low-level GPU code, and of course, browsers have very high security requirements. The second is that maintaining the types of safety guarantees that we need when composing languages is a pretty important problem. Web GPU does not generate assembly directly, rather it interfaces with native frameworks which have their own specifications and compilers before you actually get down to the code or the assembly that runs on the GPUs from different vendors. And I think this problem is actually not specifically GPU focused. There's a lot of interesting kind of new work on layering different types of languages, and I think this kind of applies to all of those as well. Okay, so let's actually get into some of the details. So what is the specification vulnerability? So first, what is memory safety? Memory safety prevents behaviors such as out-of-bounds access or use after free, and of course it's been the cause of many, many famous vulnerabilities. So if we look at this example program here in Web GPU's shading language, or WGSL, we have two memory regions, I and M, and then we have one thread, and all it does is writes I of 0 equal 2, does some independent computation, and then indexes M by I of 0. So this index into M is a potential out-of-bounds access if I of 0 was greater than 3 here. So when WGSL compilers output native language code, they actually just clamp the accesses. So here you insert a min check to make sure that you can't read out of bounds of M. However, in these native languages, you have optimizing compilers. And these optimizing compilers might notice that I of 0 is set to 2 in A, not changed, and then used in B. And it might realize that this min check is actually not needed. So when you generate GPU assembly code, that min check could be removed. And this works fine in this example because we only have one thread. But of course, when you go into multi-threaded scenarios, you have to deal with things like data races. So a data race is an unsynchronized, i.e. you're not using barriers or atomics, and you're accessing the same memory by multiple threads. And this behavior is kind of given undefined semantic in many native GPU frameworks following the example of languages like C++. So if you look at this example over here, we've added an extra thread which writes I of 0 equal to 4. And you might see the problem here. The compiler might still notice that I of 0 is set to 2 in a thread local context, so it can still remove the min check. But of course, when you actually execute this on the GPU, it's possible that you interleave A, C, then B, and you get an out-of-bounds access. So this is the vulnerability. It's a conflict between WGSL's memory safety requirements and the optimizations and specifications of lower-level frameworks and their compilers. And it's not that WebGPU didn't like fully ignored data races. It's just that these issues were a little subtle and they missed them in their specification. So because of that, we want to try and fix it. So we introduce what we call Safe Race Memory Safety Guarantee. It consists of two main properties. The first is called race-free slice, and it says program slices which contribute to memory indexing must be race-free. So if we look at this program here on the right again, there's two data races here. There's a data race between A and C and between B and C. And one way we can actually fix this using existing language constructs is atomics. So if we were to add a compiler pass which translates these accesses to atomic, you no longer have a data race in this program. And without a data race, you can no longer both optimize the min check away and have a situation where I of 0 returns 4 in instruction B. So that's the first property. The second property is called race interference, which says that data races cannot affect the behaviors of race-free slices of programs. And this actually follows on previous work by Dolan et al. From 2018, where they called this bounding data races in space. And unfortunately, this is not a property that can be implemented in WebGPU. It must be adopted by the lower level GPU frameworks. So what that actually looks like is if you see this code on the right here, now instead of indexing into M with I of 0, you index it into it with a local variable x, which cannot be shared between threads. However, this previous work showed that invalid compiler optimizations, you can end up in a situation where the x in B is set to 4, which would be bad because you read out of bounds if the min check was removed. So this property, race interference, prevents that from happening. Okay, so actually let's look at whether or not property 1 can be implemented, and if so, how do we implement it? So we did implement it in a compiler for WGSL programs using this memory logic on the left, and I'm going to walk through how we actually apply it to a program here on the right. So we'll start out by looking at this statement on line 9, which says var r equals b of x plus 1. In this case, that's represented as an access with an ID 7. It's a read access, and it's a read access to region B. And in this case, there is one what we call index dependency, and that's because x is used to access into B. Now, if we look at the definition of property 1 over here on the left under applying SMSG, we see that we say for all accesses y in an access's index and control dependencies, we must make the region associated with those accesses atomic. So in that case, we can go look at the index dependency here, which is access 6. This access 6 is the access to x itself, but again, x here is a local variable. So it actually cannot be shared between threads, so we don't need to make it atomic. And we can make it, we can mark it as safe. And this is actually where property 2 becomes important, because now we can say that because x can't be accessed by other threads, it cannot be affected by races on different memory locations, and so it is still a safe variable without even having to make it atomic. Now we're not done yet, because if you look at the second half of the property 1, it says that for all accesses z and an accesses y slice, we also have to make regions associated with those accesses atomic. And we define a slice as the transitive closure of the union of an access's index, control, and data dependencies. So basically what we're doing here is a backwards slicing algorithm through our program. So in this case, this access to x on line 9 has two data dependencies in the program. The first is this access 5, so we're going to consider that one first. So in this line, x is set to 100. Again, we've already marked x as safe here, so we don't need to do anything, but we do need to consider its slice. In this case, it has a control dependency on access 4. So if we follow that back, we end up at this line 6, which says if a of 0 greater than 5. Now, if you actually look at this program, this is dead code. A of 0 is set to 5, and it's not set to greater than 5 by this thread, so this if statement is actually dead code. But if the dead code were not removed and there was a data race on A of 0, it could end up executing, which could cause x to be set to 100. And if you had removed the min check or the clamp, then you would have an out of bounds access. So we actually have to mark region A here as atomic, and then you'd go through a forward pass and translate all those accesses to atomic accesses. And we're not quite done. We have to consider the data dependencies of this operation, and that is just this access on line 4. But again, we've already marked A as atomic, and there's no dependencies here, so we can return. The last access we need to consider is 3, which is on line 5 where you initialize x. But again, we've already marked x as safe, and it has no dependencies. So in this case, this program is finished with the analysis. And finally, because region B was not used in any of these dependency graphs, it can be marked safe as well and doesn't need to be made atomic. So that's part of the interesting kind of aspect of this property, is that it doesn't just mean you have to go through and translate everything to atomic. You can kind of do it in a more fine-grained way and still get the guarantees that you want. Now, what is actually the feasibility of this program, or of this analysis and this, this compiler pass? It turns out that it's actually it works pretty well in WebGPU. And the reason for that, one, is that WGSL programs are single source. So you have all your dependencies up front when you're performing this analysis. You're not trying to rely on linking or any sorts of complex behaviors like that. The other is that inputs to programs cannot alias. This is one of the requirements of WebGPU. If they could alias, you're basically out of luck. You'd have to translate everything to atomic. But because of this, we have a little bit of freedom. However, there are some limitations to our approach. For example, there are no atomic floating point types in WGSL yet, although hopefully they will be added soon. So our analysis and our guarantees are not complete. If you use floating points in control or data dependencies, then you might end up in situations where you could read out of bounds accidentally. And I think the other thing to kind of mention here is as WebGPU develops, it might end up with more complex behaviors. But I think it's important to consider that we might want to keep the language constrained in some of these aspects. And there's actually precedent for this in other areas. For example, there's MISRA-C for safety critical environments. And I think WebGPU, as it evolves, is going to have to keep thinking about these types of issues and keep constraining itself. So the other thing that might come up, and did come up as we were implementing, is that, okay, we're translating accesses to atomic, and we're adding these like kind of restrictions on what data races can do. So what is actually the performance impact of that? So the first thing we did is we evaluated the performance of property 1. Basically, once we've done this kind of atomic translation, what is the overhead on existing programs? And it turns out that on the applications we considered, only 2 of them actually had any runtime overhead due to our pass. And so, of course, you could probably construct pathological programs where this is really bad, but we showed that on many, many important WebGPU applications, complex shaders that use very sophisticated optimization strategies, you still don't end up with a runtime overhead. And it turns out that's because these shaders don't really have complex dependency access patterns, and they're very amenable to the type of static analysis that we support. The second thing we did is we actually checked whether or not current implementations satisfy property 2. And of course, this is experimental and empirical, so it's not formal, but we use a bunch of metamorphic fuzzing on programs, and we find that in pretty much all cases, property 2 seems to be supported by current implementations. We found one issue, but it turned out to be an unrelated compiler bug as far as we're aware. So yeah, that kind of shows that potentially these properties could be adopted by current implementations and the WebGPU specification. So in this paper, I introduced SafeRace, a set of threat assessments and language proposals to address security concerns in WebGPU. It highlights the challenges of using accelerators in security critical environments, such as browsers, and it showcases the need for more research on compositional language design. And it was presented by me. I'm a PhD candidate at UC Santa Cruz. Feel free to reach out through my website or after this talk. And I'm also on the job market this year, so also reach out if you have or hear of opportunities. Thank you.
So we do have time for a couple of questions. Please go to the microphone.
Interesting project and interesting talks. Thanks so much. You know, when we make a variable atomic, we get 2 things. One is atomicity, the other one is ordering. So is there a way to figure out which one we need, and if we need ordering, can we insert fences at the right places?
So yeah, I glossed over that in the talk, but we use relaxed atomics completely. There's no need for any ordering in this situation. So we're mainly worried about the atomicity and coherence properties of the atomics versus the ordering kind of things that they provide.
This sort of mismatch between the 2 interfaces. Have you thought about establishing the absence of, I'm thinking specifically of compiler mappings, where you think purely in terms of
Yeah, I think that's kind of where this all broke down to begin with. And the reason for that was like the undefined behavior in the lower level frameworks. So like WebGPU tried to give some semantics to data races and thought about all the compiler kind of paths that they could take, but the undefined behavior, of course, will always come back and bite you. So I think it maybe be a bit controversial, especially for C++, but my kind of opinion there would be that these lower level GPU frameworks might want to remove undefined behavior completely, because then you might be able to do this kind of proof. But I think in the current situation, you're always going to be able to find these paths for other types of undefined behavior too.
Okay, thank you.
Last very quick one. Yeah. You need source code to do all this analysis. is there in cases where you don't have the source code and you have to do it without having source code? I mean, close libraries.
Luckily, another reason, WebGPU, it all is kind of compiled in the browser at runtime. So you do have all the source code at that point. That's something, if they want to add that in the future, some sort of closed source libraries or binary formats, they're going to have to think about that. Hopefully this work helps them think about that.
Okay.
Okay, thank you so much. So our last talk of the session, and at last, undefined behaviors.
This talk will go over the thin air problem and a solution to it. So the thin air problem is a long-standing problem across all optimized concurrent languages, and a solution should meet the following criteria: that it corresponds tightly with existing optimizations and litmus tests, that it's executable so that the litmus test can be evaluated, and it should integrate cleanly with existing declarative memory models. And our model SMRD solves this. So now we'll cover some background that's needed to understand the thin air problem. We'll be using programs like this throughout the talk. Here, if something starts with R, it's a register, so it doesn't have memory associated with it. And otherwise, it's a global, and it's an atomic memory location. And these are concurrent programs. They're executing together. And we also have diagrammatic representations of these to explore executions of the program. So sequential consistency. This is the intuitive view of concurrency, where we have thread events interleaved in a total order. And the syntactic program order is a subset of this total order. And the thread is connected by these RF arrows, which connect writes to the reads that read from that write. So what are the possible values under SC? We can read before we do any writes. We can perform one write before we do a read, and like this, but we cannot have the outcome of 1-1 because this requires us to perform the writes before the reads, and we get this cycle, so we no longer have a total order. But then here comes along weak memory. This allows this outcome, and it does it by relaxing one of the constraints. This is also why it's sometimes called relaxed memory. And in this case, we can relax the constraint that our total order, that program order is a subset of our total order. So this arrow on the left, we can switch around our ordering, and now we no longer have a cycle, and this is allowed. So the C++ standard has a weak memory model. So what happens if we have an execution like this? Well, we can pluck any value out of thin air. And the reason this is allowed is because cycles in union, program order union RF are allowed. And that's what introduces these values. And the reason this is a problem is because this 42, there isn't really a way to reason about the behaviors that are introduced from this, because there isn't a good reason for 42 being there. And these thin air values can happen even when writes depend upon these. You see these orange arrows because we're taking the values from R1 and R2, but they're supplied also by these. So these shapes should be forbidden. And disallowing these thin air executions while still allowing compiler optimizations is the crux of the issue. And this is what we'll be solving. So one of the ways that compilers optimize is by assuming that undefined behavior never executes. So in this example, we know that division by 0 is undefined behavior. So therefore, both us and the compiler know that not R1 cannot be 0. So the only other value is to say that R1 is 0. So we do this rewrite, and then we can simplify it to a constant. And you see on the left, we have a dependency on R1, and on the right, we have no dependency. So this optimization has removed a dependency here. So putting this in the wider context, we now have T1, which looked like the previous example, and now we have T2 that does some stuff with X and Y. And now we have a shape that looks oddly like our thin arrow example from before here. But we don't have this dependency edge because we're allowed to optimize away the state dependency. And GCC and Clang also think this behavior should be allowed. So that's good for us. And this doesn't look too good, but on line 3, we see that this store of 1 divided by not R1 has been optimized to a move of a constant 1. So it is doing the optimization, so we can observe this behavior. And now we'll go more into the details of the model. So for every write in an execution, we must justify it. So we have this justification structure here that has control dependencies and data dependencies associated with it. And then we have a set of elaborations, which are operations that alter these to produce new justifications. And we also have these program-wide guarantees that aren't part of the justification but sit alongside them, and they capture information about the program. And elaborations can weaken control dependencies with these. So if our program-wide guarantees imply some control predicate, we can remove that because we know this information without having to actually execute. And now we'll go into the example from before, but using the justifications. So we create an initial justification for this write 8, and we leave it as is. This is a true dependency, so we'll just leave that there. And then we create an initial one for 3, and we have a data dependency on R1 here, because the expression 1 over not R1 contains R1. And from here, we can perform a strengthening elaboration. This adds a control dependency. In this case, we'll choose to add R1 equals 0. And this simply means that this write happens in fewer executions. So this is fine to do. And now we have value assignment, which uses information the information about how values are constrained by the control predicate, the control dependencies, to rewrite values in the expression. So here we know that R1 equals 0, and we have R1 here. So we can rewrite that R1 to a 0, and we have now transferred the data dependency of R1 into a control dependency on R1. And this simplifies like the previous example into this justification. And now we can perform weakening, which is the operation that we talked about before. With the program-wide guarantees, we know that R1 must be 0 because of the UB freedom. And we can now remove that dependency, and we get this independent write, which justifies the execution that we saw before. So we've removed this dependency. Okay, and now onto our tool. So this tool allows us to explore the executions of the program under our model. You can see here that this structure on the right matches what we saw in the slides. and that this execution is allowed by this. And I started running the tests a second ago, and we see that it's finished. Yeah, the performance of the tool is quite good, and it also handles code with allocations, which former tools could not. Now, in conclusion, we have a solution to the thin air problem, and you can try out the tool by scanning the QR code. That's all.
So we do have time for questions.
Hi, thank you very much for the talk. Yeah, I'm Anton Tkapaev. So a couple questions. This is not the first solution to thin air problem. I mean, to some degree. I heard about some of them. So how it compares with everything else, like from promising, for example?
So this example about UB freedom, in the initial case, the only time where the undefined behavior happens is when R1 is not 0, right? But the only way for that, and it is always 0 if these are ordered. So the only way for it not to be 0 is to do the optimization, which prevents the undefined behavior. Mm-hmm. This is what allows this execution to happen. In promising, what we see is that you can see it, you make the observation that you can do the optimization into a store of a constant 1. So you can you successfully can make that promise. You execute the other thread. You perform the transaction of writing that 1 back in, but then you re-perform this computation. So the rewriting isn't consistent, and then you observe the undefined behavior. So you can have any outcome in this case. So you can introduce a thin air outcome. So in that case, introducing undefined behavior is one way in which promising doesn't quite match up. Does that answer the question?
Yeah, I guess we'll chat a bit more after. Do you have more time? So one other thing I was wondering, so like in the first version of MRD, like I saw a problem that like basically needed to consider all possible values to make a read, for example. Is it still the same here, or you did something about that?
Yes, I think I skipped over like the main contribution to this is that it's symbolic. So the like concrete event structures we had before, where it would split on the reads, like read x1, read x2, up to however many. This is now constrained by symbols, so we don't need to do this concretization. Yeah.
Great, thanks. Yeah, let's chat more.
Yeah.
I was curious about the interaction between sort of out of thin air and undefined behavior. So I think there's this example by Mark Batty that shows that sort of you can have undefined behavior that causes itself by undefinedly spawning another thread that does a load buffering shape. So how do you address this?
I'm going to answer this twice in 2 different ways. So the first one is if there undefined behavior, you can do anything, right? So there's 2 cases. There's one where the code doesn't actually have that thread spawning capability, but because you hit UB, you can now introduce thread spawning. Then there's a case where you can spawn a thread in the code, but you can only access it through doing some UB stuff. In the case where the code doesn't exist, we took an approach to UB, UB freedom, in that the assumptions we make are that it never happens. If you actually reach UB, then all bets are off. In that case, like for example, if this could be 1, let's say it was initialized to 1, then you could actually execute that, and any execution is allowed anyway. So in the case that it doesn't exist, we wouldn't have this problem. In the case where it does exist, if you could spawn a thread through actually executing UB, then that is a fine thing to do anyway, because at that point you can do anything, right?
Yeah, so maybe this is best taken offline. I mean, I don't know, you have 200 tests, I have 200 questions.
Okay.
Okay. So let's thank the speaker again.
Test. All right, welcome everyone. Welcome to the abstraction session, where every paper in the session has the word abstract somewhere in the paper. And I would like to start by introducing our first speaker, Miha Nikola, who's from Stevens Institute of Technology, and he's going to talk about an abstract interpretation of temporal safety effects of higher order programs. Thank you, Nikola.
Hello, everyone. This is a joint work with Chaitanya Agarwal, Eric Köskinen, and Thomas Wyss. In this work, we studied the problem of verifying that program traces satisfy a safety temporal property. This problem arises in applications such as input-output behavior, resource access analysis, and others. And the challenge is, can we do better at automatically verifying these properties? In this case, program traces are sequences of observable events. I'll explain that in the next slide. Let's consider this example that models an auction process. It has three parts: bid, close, and refund, and it's a higher order. The program execution starts with calling bid. On the right side, I will show the events generating during the execution of this program. Bid places a non-deterministic number of increasing bids, and for each bid, it emits event 1, corresponding to a bid event, and it also constructs a delay computation corresponding to refunding of the previous bid that was overtaken for the new bid. Assume that it does that 42 times, and then close the bidding stage. It calls the close function, emits event 2, and then in turn calls the refund of the last losing bid, which then calls in cascade the refund of the remaining non-winning bids. The program trace for this execution is these 42 bid events followed by a close, and then 41 refund events. And the program traces for, and the event traces for this program are defined by this context-free language. Even though in our example the events are constants, an event can be an expression which is first reduced to a value and then emitted as a side effect. And the operational semantics is defined in terms of pairs of program expressions and sequences that are observed during the evaluation. The property that we are interested in states that the stages of the auction occur in correct order, and the number of refunds are at most one less than the number of bids. Since we cannot express this with the finite automata, we use a symbolic automata with accumulator. Transitions in this automata are defined in terms of guards and updates of the accumulator. For this property, we use two accumulators, a bid counter and a refund counter. And the automata states that under the bid event, it self-loops to Q0 and increments the bid counter. Under the close event, transitions to Q1, where it self-loops under the refund event, incrementing the refund counter, provided that the relation between the bid counter and the refund counter holds. Otherwise, it transitions to the error state. Notice that the accepting state is the error state. Therefore, the property expressed by this automata is actually the complement of the language recognized by this automata. So we need to verify that the intersection with the event traces is empty. We can take the immediate approach and reduce this problem to a search and checking in product of the program and the automaton. And we can do that by encoding the automaton in the programming language, and then we perform a transformation on the program by passing the automaton configuration in and out of each expression, weaving it through the program, replace the EV expression by a call to a transition function, and finally we add the assertion on the final configuration. Then we can use the existing automated verifiers to verify this eventless program. However, they struggle. There are a couple of problems. First, weaving the automaton through the program increases the arity of the functions, and that impacts the performance of the underlying solvers for predicate synthesis. Then we have longer analysis because of the program blow-up. We have burden on the type system, and then also for verifiers that are based on refinement types, the lack of precise joins or the lack of disjunctive reasoning may lead to failure to verify because the transition relation is encoded as the sequence's if then else expressions. Another approach is via type and effect system. A proof is a valid derivation in the type and effect system. And in prior work, we have seen solutions where effects have been represented in terms of automata, omega regular expression, predicates in a fixed point logic, and other works have been focusing on algebraic characterization. In all these works, effects can capture both finite and infinite behavior, so they can reason about properties which go beyond safety. The great thing about is the compositional verification. The downside is that they're not fully automated. That leads me to introduce our work, which is a new method for scalable effect inference, which is grounded in abstract interpretation. In the next part of the talk, I'll introduce a novel abstraction of temporal effects, which are based on symbolic automata with accumulators. I'll show how we can embody these abstractions in the novel accumulative type and effect system that provides the proof, and I'll show our implementation and our evaluation results. Let's begin. The key idea is that in the concrete semantics, we can relate event prefixes with environment valuations. Let's see that by zeroing in on the bid event in our example. Before reducing the EV1 expression in the environment, we have several variables. Let's focus on the environment variable I. And the event trace prefix at this point is empty. After the bid event is emitted, event sequence now become 1. And notice that the number of occurrences of 1 in the event sequence is equal to the environment variable I. We can see better after the second bid is placed, and the same invariant holds after each bid event. Accordingly, we exploit this by modeling the concrete effects as sets of pairs of environment and variables. I'll walk you through the construction of our abstract domain for effect by using the bid event as example. The first observation is that we can represent the event trace prefixes by reachable configuration in the property automata. Effects in our first domain are exactly that, sets of pairs of reachable configuration and environment valuations. Next, observe that we can exploit the structure of the automaton, and we can partition this set by the control states. However, these partitions are infinite. That's untractable. So in the next step, we abstract these partitions by elements of a relational numerical domain, such as polyhedra, octagon, and so on. So for example, the mapping from Q0 to this set of relational constraints says that represents all the event trace prefixes that end in, whose run on the property automaton end in the control state Q0 with the accumulator value which is constrained by this set of constraints. And the other states are mapped to bottom, and that means that have not been reached. So our effect domain is the domain of these SAA abstractions. We have formalized the domain, as a composition of Galois connections defined for these domains. I'll skip over the technicalities. Please see our paper for the full details of our construction and the soundness proof. Next, I will show you how we can take this abstraction and embody in the cumulative type and effect system that provides the proof. For this typing judgment, on the right side, we have the typing context gamma and the effect context phi, which summarizes the prefix traces up to the evaluation of the expression E. The expression E dictates how the extension is being formed, tau is the refinement type, and phi prime summarizes the extended trace prefixes with the evaluation of E. For example, this is the typing rule for a single event where an event value is appended to the trace prefix. And this is soundly abstracted by this effect extension operator, which we require to be defined in the effect domain. Let's build this intuition by looking at the inferred effects for our bid event. This typing judgment corresponds to the conclusion of the rule. In the context, the effect says that only Q0 has been reached and the bid accumulator is 1 less than the environment variable I, while the refund accumulator is 0, and then we have other relational constraints in the environment. And Q1 and Q0 has not been reached. Recall that under the bid event, the automaton transitions back to Q0 and increments the bid counter. So the extended effect reestablishes this invariant that the bid accumulator is equal to I. And on a side note, the refinement type for the EV1 expression is the refinement type for the unit val. Next, I'll talk about our implementation and evaluation results. We have implemented a prototype, EV drift, for OCaml programs extended with EV expressions. It builds on existing abstract interpretation inference of refinement types, and we have improved the precision of the analysis by adding support for trace partitioning. And we have shown that our method can verify a wide range of SA expressible properties, such as tracking disjoint branches of a program, resource analysis, verifying a reentrant lock, tracking bounds of a variable, amortized cost analysis for a two-list implementation of a queue, or also cost analysis for binomial heap, monotonicity, and others. And we asked the question, how did we do? How effective is EV drift compared with existing tools when they're applied on the reduction that I showed in the first part of the talk, where we transform the event-full or effect-full program into an eventless program. Out of the 23 benchmarks, Drift managed to verify 12 with a geomean of 1.9. OCaml verified 6 with a geomean of 1.6. Mochi 11 with a geomean of 6.7. RETHFL 18 with a geomean of 5.1. While EV Drift managed to verify 21 with a geomean of 0.9. So in summary, we've introduced a first abstract interpretation-based approach to verify safety temporal properties, a novel effect abstract domain with increased support for disjunctive reasoning, that it's embodied in a novel cumulative type and effect system, and we have shown an effective implementation that can verify a wide range of SA expressible properties. Please see our artifact here. Thank you.
We have time for a question. If you'd like to ask a question, please come to the mic here. And identify yourself and your affiliation, please.
Hi. Thanks for the great talk. So I want to ask the question about the accumulative type and effect system. So it seems that the phi and phi prime are somehow specialized to the specific automaton. All right. So I'm wondering, you consider abstracting such a state of the automaton to reuse the verification result to other automaton or other setting?
Thank you for the question. It's a good question. I think one of the reason the accumulative type effect system is able to work is that the effect domain is actually not compositional. This is like a whole program analysis. Whether it works with other automata, I think it can work, because as long as you maintain this whole program analysis constraint.
Our next speaker is Vaibhav Mehta, and co-authored with Justin Chu from Cornell University. And Vaibhav is going to talk to us about a Hoare logic for symmetry properties. Thank you.
Thank you. Hi, everyone. I'm Vaibhav, and today I'm going to talk about Hoare logic for symmetry properties. So first up, what is a symmetry property, and why should you care about that? Well, to answer that question, I'm going to go through a series of motivating examples. So first, let's consider a voting system where you have two candidates, a cow and a duck. And suppose you have 3 voters, and they come in and they cast their vote one by one. And suppose we declare the cow as the winner of this election, and you use some method to decide this, doesn't really matter. And now you want to verify some correctness property. There's many correctness properties for such a voting system you might want to verify. But one property you might care about is anonymity, which is to say that the identity of the voters should not matter, right? And the way this is typically formalized is we say for any permutation of the input or for any permutation of the voters, the output or the winner of the election, which is the cow, remains unchanged. So in this example, we're interested in a family of transformations on the input, which is all the permutations, and the effect that they have on the output, which is invariance. But in other settings, there's other transformations we might care about. For example, suppose we wanted to verify a cyber-physical system. Specifically, imagine you have a car that's trying to reach some destination or waypoint, and it's just traveling in a straight line. And now you want to prove some safety property about this system. Now, in general, this can get quite complicated. So one trick researchers do to simplify their reasoning is that without loss of generality, they assume that the destination of the waypoint is at the origin or at 0, 0. Now, this is useful because knowing that this is 0 lets you simplify any program expression verification condition which mentions this. But another interesting question is, why is this sound and when is this sound? Well, in this case, it's sound because this program preserves translations on the input. Meaning, if I translate the car by some amount, with the starting position of the car by some amount, and I run the program, or the car moves in a straight line, the final position preserves this translation. So translating the car's position by some amount leads to the same translation on the output. And this could be any translation. So here again, there's a family of transformations, which is all the possible translations on the input, and the effect that they have on the output. So we see that this notion is useful as a correctness property, and it's also useful as a way to simplify proofs. And our goal with this work is to formalize and verify such properties. And to that end, we have 2 major contributions. The first is a program logic for verifying these symmetry properties. For this, we develop a novel assertion language using ideas from group theory, which I'll explain in the next few slides. And then we develop some Hoare-style proof rules for reasoning about these assertions. And then we have a prototype implementation, which we use to automatically verify such properties on real examples from across the literature. So in this talk, I'm going to focus mostly on the first contribution, which is the program logic. And to do this, I'm going to give you some group theory background, but I promise it's not that bad. So a group is a set G, which is endowed with some binary operation, which we call group multiplication. And we have some axioms that this operation is subject to. The first is we demand that this operation be associative. The second is the identity axiom, which says there should exist some element E in the group, such that this element E multiplied with any element just gives you the element itself. So this element does nothing. And the third is every element should have an inverse. So for any element A, there's an element A inverse, such that if I multiply the 2, I get the identity. So an example of this that maybe we're all familiar with is the group of integers. Under addition, they form a group because, well, addition is associative. 0 is the identity because a number plus 0 is just the number itself. And the negative of a number is its inverse because a number plus the negative is just 0. So groups are great, but what we really care about is the transformations that they induce, specifically the transformations they induce on program states. And this is captured by a notion called a group action. So a group action is of a group G on the set of program states is a map or a function A that takes in a group element, a program state, and it spits out a new transformed program state. And we require this map to satisfy some axioms, but for this talk, those axioms aren't really important. So if we take the group of integers, let's think about how it might transform program states. Well, it might transform a program state by adding integers to the variables x and y. And so we'll denote that as follows. We'll write the name of the group, which is the integers, the name of the action, which I'm going to call add for addition, and I'm going to say that it's going to modify the variables x and y. And the way it's going to do this is it's going to take in an integer n, take in the variables x and y, and add n to the values of x and y. So in our paper, we define a flexible and compositional syntax for defining these group actions. So they're not actually built in like you see here, but rather you're free to define your own transformations. And these will serve as assertions in the logic. So now that we have the assertions, we can move on to actually defining the logic and seeing what it looks like. So this is what the triples in our logic look like. And the key difference from our logic and whole logic is that the pre and post conditions are now group actions. So we have a precondition group action G, GA, which acts on the input. And we have the program, and then you have a post-condition group action HB that acts on the output. And intuitively, a triple is valid if for any transformation on the input by GA, there exists a transformation on the output by this group action HB. Or in pictures, this is what it looks like. If I start with some program state sigma 1, apply the any transformation from the group action GA to obtain sigma 2, and then I run the program C. If this is the same as just running the program C and relating the output, and I can relate the output of running the program C via the group action HB, then this triple is valid. And so this is roughly what validity in our logic looks like. And so for the rest of this talk, I'm going to explain how you can use our logic in what I think is a fairly intuitive way to verify symmetry properties. And to do this, we're going to verify a small toy program. Specifically, we're going to consider this simple program which models a car moving in a straight line. So we have a for loop here that runs for capital T time steps, and the loop counter variable small t is incremented by some small constant dt, which represents the time passed per iteration. And so in the loop body, for every iteration, we update the positions of the coordinates of the car, x and y. And the way we do this is we take the velocity along the x-axis, multiplied by dt to get the amount we've moved along the x-axis. And then we add this to the old position of x to get the updated position of the car along the x-axis. And we do the same thing for the variable y. And so if you just keep running this loop, you get a car moving in a straight line as the x and y coordinates modify. And we want to show that this car moving in a straight line preserves translation, meaning if I add any integer to the variables x and y when I start this program, and then I run this program, at the end, the positions of x and y will still remain shifted by by any integer that I started with. And so, how do we prove this? We'll use rules from the logic, of course. And to start with, I don't like the for loop, so we're going to try to get rid of this. And how are we going to do it? Well, our logic has a for loop rule, or we also have a while loop rule, but here is a stylized version of our for loop rule, which says that if a command C preserves the group action, meaning it has the same pre and post condition, then running it for t time steps will continue to preserve this group action. And this notion of preserving a group action here is our analog of a loop invariant, essentially. So now our only proof obligation is to prove the stuff above the line, which is we need to prove our loop body actually preserves the group action we care about. And so how are we going to do this? Well, this is our loop body, and we're going to apply rules from the logic to try and fill in all these blanks. So let's start with the precondition that we care about, which is the addition group action. And now we have an assignment statement, right? And so we should apply the assignment rule from our logic. And indeed, we do have an assignment rule in our logic. I'm not going to spell out the details of what of how this assignment rule works, but I hope you'll believe me that it gives us some intermediate group action, which I'm going to call B, which is still a group. It's still the action of the group of integers, but it's maybe doing something different to the program state, and it's still modifying the variables x and y. And so now I have this intermediate assertion B, and I'd like to be able to string through a sequence of judgments and talk about the post condition of y. But to justify this sort of thing, I need a sequencing rule. And so similar to regular whole logic, our logic also has this. And the sequencing rule says if a command C1 has the same post condition, if this command C1 has a post condition that is same as the precondition of some command C2, well, I can just sequence them together and get a larger judgment. And so now if we go back to our program, I can start with this group action ZB as my precondition for Y, apply assignment, and now I get this new group action that's somewhat mysterious, which is this group action I'm going to call C. And then by sequencing, I can justify this big judgment, which says, okay, that the loop body, if I start with the group action add, I get some group postcondition C. And maybe this is a bit troubling, right? Because we want add in the postcondition. So what do we do now? Well, in standard Hoare logic, you check to see if there's some entailment or implication thing you could do. And our logic also has a notion of entailment. So a group action GA implies another group action HB if the group action on the right, HB, contains all the transformations in GA. So essentially, if HB is a bigger group action than GA, we can say GA implies HB. And so using this notion of entailment, in our logic, we define a weakening rule, where if you've proven some triple GA CHB, you can prove that HB implies some other group action IC. You can always weaken your judgment to say that I is the postcondition. And so it will turn out in our setting that this group action C that I have not defined actually implies the addition group action that we care about. And so if we use weakening, we can essentially prove what we wanted, which is that the loop body preserves the addition group action. And so putting it all together, this is what we've shown. If you add some integer x and y, some integer to the starting positions x and y, and you run this program where the car moves in a straight line, you will end up in a situation where the final position of the car is translated by the same amount. And so this is what a lot of the proofs in our logic look like. They're very similar to Hoare-style proofs. And so just wrapping up, in this talk, I presented a novel program logic for reasoning about symmetry properties. The key insight was we use group actions as a way to formalize assertions, allowing us to express many transformations in one go. There's lots more in the paper. There's lots of structural rules that take advantage of group theoretic structure. Groups have a lot of mathematical structure where they're able to exploit to have some interesting structural rules using group products. We define weakest precondition in our setting, and we show under certain conditions it exists, under certain conditions it doesn't. And based on our weakest precondition, we actually implement all of this in a tool which we use to automatically verify many symmetry properties. And of course, our artifact is available, etc., and all that. And I'm happy to take any questions. Thank you.
If you could introduce yourself before your question.
Jules, undergrad in NUS. I think it was very interesting. One question, I think it might be quite common whereby like a part of the program doesn't preserve a group action, but another part of the program reintroduces a group action. So like how does this get handled in your system?
I see. So when you say, I guess, sorry, there's two issues here. One is, it's in our system, it's fine if it doesn't preserve the same group action. So our rules may not always give you the same group action. So you can start with some group action, and you could end up with some different group action as an intermediate assertion. And then maybe at the end, you'll end up with the group action that you want if the property holds. There is this other issue of sometimes there may not actually exist a valid group action in the forward direction, which is why often we have to do backward reasoning in our system, which is where the weakest precondition comes in. Because in the backward direction, there always exists at least the identity, the trivial group action. So that way we're able to kind of avoid this sort of issue. But that's a good question. Thank you. Thanks. Yeah, thanks.
So, let's welcome our speaker, Shushu Wu from Shanghai Jiaotong, who's going to speak about encoding the for all exist relational Hoare logic into standard Hoare logic.
Thank you for the introduction. Today it's my pleasure to present our work about relational logic here. I'm Shushu from Shanghai Jiao Tong University. This work is done together with my classmate Xu Wei and my advisor Qin Xiang. So let's start by how we prove program correct. Here's a very simple example. Add one function that takes x and returns x plus 1. Then we can describe it using a whole triple like this. It says that the return value equals to the argument plus 1. Then we can use verifiers to prove this triple, such as heap and seek, pharmacy, and the verify software tool chain. In our lab, we choose VSTA, which is an annotated verifier built on standard separation logic. Then we can annotate the code like this, and our verifier VSTA will check that this triple holds. But real program aren't that simple. When we want to prove a program respect to its functionality, that is what's supposed to accomplish for us to use, we will introduce a formal model to describe what the code is meant to implement and layer our proof into 2 stages. Here, the low-level program uses a bit OR to record the elements in an array A, and the high-level program uses bit union to record the elements in a list. So in the first stage, we will prove the concrete code refines the formal diagram description, and in the second stage, we will prove the formal diagram description itself is correct. So like this, 2-layer proof, once both are done, we can combine them to conclude that, oh, our code is correct. So this layered approach improves modularity and proof reuse. So we might ask that, can our existing verification tools handle such layered proofs? If we look closely, we find that we need to reason about refinement between 2 programs. Refinement says that for every observable behavior of the low-level program must also be a possible behavior of the high-level one. Relational logic can capture this idea. It is well suited for reasoning about such relationships. And if both programs are deterministic, the for-all relational logic is sufficient. But if one program is non-deterministic, then we need to use the for-all-exist form. There are some existing frameworks for all-exist relational logic. One popular is the relational triples. Here, we treat high-level program as resources. Here, the assertions are not only about the program states, it includes the information about the high-level program to be fulfilled. In this relational triple, it says that for any given low-level state and high-level program, for any final state of the after execution of low-level program, we will find some multi-steps that the high-level program can achieve, and that the post-condition satisfies. Then, using such a relational triple, we can represent a program refinement like this. Here, in the post-condition, skip represents that the program has ended. So, building a new relational verifier is a choice of ours, but we want to reuse our existing logic tools instead. How to? We can encode it into standard logic. It is known that the for-all-exist form can be encoded into a logic with ghost states and invariants. In this logic, it says that for any update of the physical states, there exists a way to update the ghost state such that the invariant holds and the 2 states can be updated continually or terminate at the state satisfying the post condition. But if we extend our tool to support this rich logic, we will redo our soundness proof, and ghost update will break the conjunction rule, which is bad. So our work aims to enable standard logic tools to express and prove for all exist properties directly. Let's take a quick look at how our approach works. For the bit mask example, we can use this relational triple. It states that before execution, variable A stores an array L, and variable n equals to the length of L. And after execution, the return values encode the elements in the high-level return value as a sum or powers of 2. Then we can use a logic variable L to decompose this assertion. like this. To decompose these assertions like this, then the first part with the floor rotation is only about the low-level state, and the second part is only about the high-level state. So our work can encode such decomposed forms into standard whole triples like this. We found that here the low-level part remains the same, while the high-level parts are encoded into an execution predicate, here with the blue color. This execution predicate is the core idea of our encoding. Actually, our encoding defines an assertion encoding function. It transforms a program a resource assertion into a low-level assertion and ensures that a relational triple is valid if and only if the encoded standard whole triple is valid. For more detail about the definition and the proof, please refer to our paper. Especially for the decomposed assertions, we can encode it into an execution predicate. Here, the logical pure condition B it keeps as the same, and the low-level part remains the same. Here, the execution predicate intuitively states that there must exist some initial state satisfying P such that the final state after execution C satisfies X. Now we can express refinement with whole triples, but how we can use whole rules to prove such triples. Let's see how we encoded the rules. Here is a one-side rule for the low-level program. It states that we can independently evaluate the first part, C1, of the sequential composition. After our encoding, it looks like this. If we ignoring the execution predicates, the rule exactly is the sequencing rule in whole logic. So we know that for the low-level part, we can just use the whole logic in the standard whole logic rules. For the high-level side, this rule states that we can independently evaluate the first part C1 of the high-level sequencing composition with an angelic whole triple. This angelic whole triple says that for any initial state satisfying P, there must exist some final state satisfying R. So after encoding, we find there are two standard whole triples in the rule, where the premise triple weakens the precondition of the goal triple. This is just the consequence rule. Now we are ready to prove our example. Here we write precondition we require and write postcondition with ensure. This is exactly the whole triple we see before. Then for the first two assignments, we can freely use our two symbolic executor and we can obtain these assertions. That is, we know X and I both equal to 0. Then before step into the while loop, we need to align the two programs. That is, we need to proceed with the first two high-level statements. To evaluate this high-level assignment, we need to see a sequencing rule for the execution predicate. This is provided by our work like this. Then using the sequencing rule, we can freely evaluate the first high-level assignment. This gives us that S equals to empty. Then we can do the same for the variable J. Thus, we can write this loop invariant. It shows that the corresponding between the data of two programs, S equals to 0, and S equals to L 0, and X equals to sum of the power of 2 for each element in L0. Here we notice that the high-level program in the execution predicate is a sequential composition of a while loop and a return statement. This is because no matter how many iterations have been finished by the low-level program, the high-level program to be fulfilled is always a sequential composition. Now we see how to prove the loop. One step inside the loop body, the symbolic executor will give us that M is smaller than the length of L. This allows us to unroll the high-level while loop like this. Here we add two assignments before our loops. Then we can use the techniques as before. We can evaluate the two assignments in the low-level body and then evaluate the assignments in the high-level program. And thus we get our program correct. In conclusion, to enable horological tools to prove for all exist properties, we present an encoding theory that reduces for all exist relational logic to standard logic. Specifically, we introduce a simple predicate, execution predicate into logic, and we provide substituting rules. And by doing so, we won't reprove the soundness, and we can use whole rules and automation tactics like the symbolic executor. And all the meta theory and case studies are implemented in ROC. Thank you for your attention, and I'd be happy to take any questions.
Hello, I'm Vova from NUS. Yeah, thank you. Very nice talk. I wonder, like in the example you show, you basically have the while loop in the high order program is in a sense aligned with the while loop in the low level one, right? So they have the same number of iterations. So I'm wondering if you have considered cases where, well, these kind of loops are not aligned, and one is, for example, one step of one while loop corresponds to 2 steps or like more steps of another one. And yeah, have you considered this kind of programs, and do you have any special techniques to reason about such things?
Yeah, it's a good question, thank you. We have considered such cases, and this is because of we use program as resource triple, so the while for the while loop, the loop invariant, we just need to say for when, no matter how many iterations the low-level program have finished, we need to identify the remaining programs that the high-level program corresponds to. So for this example, if here we write 4 assignments in the high-level programs, then the 2 loops are not aligned, but we can also use this loop invariant to prove this example, to represent the remaining iterations that should be fulfilled by the high-level program.
Okay, thank you.
Thank you.
All right, let's thank our speaker. So our next speaker is Guanyan Li, and he'll be speaking about structural abstraction and refinement for probabilistic programs. Thank you, Guanyan.
Okay, thank you. Yeah, hello everyone. Good afternoon. I'm Guanyan Li. It's my pleasure here to present our work, which is co-authored by these authors. And in this work, we introduce new abstraction refinement methods dedicated to probabilistic program verifications. So I would first like to introduce the problem we studied, which is the probabilistic threshold problem. Well, so this symbol mimics the whole logic representation, and this triple I think you have already known about, so I will abbreviate the explanation. So so ultimately, our interest is about to inquire if the violation probability is bounded by this threshold. And there are now many existing techniques to handle this problem, and such as program synthesis, predicate abstractions, and so on. And we would like to introduce a new framework called structural abstraction for this problem. So let's introduce an example to illustrate the problem more concretely, which will also be used throughout this talk. The program can be interpreted as a coin flipping game between the 2 players, and say Alice and Bob, and they make an initial toss, and if the heads down, then Alice wins immediately. Otherwise, Bob will choose a number of rounds, say C, to continue. And then Alice guesses that no heads up will occur during this round. So the variable x then tracks this heads down events, and Alice will win if the post condition x equals 0 is met. So the violation probability means Bob is winning. And this probability of Bob winning is capped by 0.5 as c tends to infinite. So then we're going to introduce the core insights of this work, which stems from a non-traditional observation of the relationship between the probabilistic control flow automaton and the Markov decision processes. Here, the PCFA is a common graphical model for representing the probabilistic programs. For this example, the program we just saw can be represented by this PCFA. So one of the most widely adopted relationship between the PCFA and MDP is that the MDP represents the semantics of the original PCFA. So more specifically, the state space of the PCFA. So for this specific example, the MDP will become like something like this. So we first mark the locations in the PCFA to have a more concrete explanation. Then the program states of this PCFA are then tuples representing the locations, value of c and value of x. So for the initial state here, where the location is 1, then with some fixed value groups of c, then we can see here something c is 2, c is 0, or c is 5, and then with infinite number of x here. Then after the action of assigning x to 0 here, then we'll get to the location 2, where the x is fixed to be 0, and the c can continuing being any. And with other actions here, the 0 action here with distribution, and then we'll get either to the left branch that assigns c to be 0, or the right branch where that's nothing. And well, obviously, even for this very simple example, the semantics MDP is of infinite states as the initial value of c and x are unbounded. So instead of this formal approach, we in this work propose a new relationship between PCFA and MDP called structural abstraction. So the insight is that the structure or the shape itself of this PCFA is very much like an MDP, like this. We can change this structure, so as compared to the original PCFA, where that the nodes in the, or the states in the MDP corresponds just to the locations back to its PCFA. And actions in the MDP corresponds to either the distribution tags, say the 0 and 1 here, and, or just simply the statements. But notably, now the statements are pure action labels without any computational semantics, as it's just MDP, which is emphasized with these angle brackets here. So instead of computation, they now becomes pure non-deterministic choices of the MDP. This is, I think, is an intuitive correspondence that it should be straightforward to observe. Every PCFA could have a unique underlying MDP via this way. Then back to our question, how does this insight help us with the probabilistic threshold problem? So the key is that the structural abstraction gives us an upper bound for the probabilistic violation probability. So let's first mark the pre and post condition here. And more specifically, let us mark these starting and ending states of the MDP. So the structural upper bound is just the maximum reachability probability of its underlying MDP, which means from this starting to this ending location, and this structural upper bound is now trivially 1. We then call this the structural upper bound of the violation probability. this should be a straightforward observation, as the transitions in the MDP are an over-approximation of the possible executions, safe or unsafe, of the PCFA. Namely, it considers simply all the possible traces in the PCFA regardless whether they are safe, unsafe, or even impossible to execute. So let's here consider some examples. Let's consider this trace. So I think this trace here, it becomes blue here. I think it's not that obvious. So this is surely a safe trace, as it assigns the x to be 0 and then get to the end without modifying anything. So, but this MDP may surely count this as contributing to its tributary 1 as structural upper bound. And we may even have this trace. Well, I think the color here is not that obvious. So, yeah. This one is even worse because it is infeasible. Namely, there could not be any actual execution of this trace in reality. Notice this. So the C is assigned to be 0, and then it assumes C to be larger than 0. So this could never happen. And we call these traces the non-violating traces. Now that we know the initial structural obstruction is very coerced with a trivial upper bound of 1, and the reason is because the existence of these non-violating traces, it becomes natural that we simply can refine this structural upper bound by refining the automaton by eliminating more these non-violating traces. To this end, we introduce the principles of the structural refinement. The key idea is just to construct a new automaton here, denoted by V here, that simulates the violating traces of the original PCFA. Then by the standard automaton operations, the intersections in deterministic minimization here, we can establish a refined PCFA with the same violation probability as the original one, but with less non-violating traces. A notable point here is that the construction of V is totally irrelevant to the probabilities and can be done purely with the established non-probabilistic techniques. Namely, the V here, there's no probability. So to grasp this sense, we here present an example here. So this is the safe trace. We adopt the renowned technique of trace abstraction. So this involves the interpolation and the formation of the Floyd Hall automaton. We can first interpolate it. So this interpolation simply serves as a proof of why this trace is safe. That after x is assigned to 0, there's no statement to change this fact, and hence it will eventually become x equals 0, and hence it's safe. And then we form a Floyd Hall automaton from these interpolants by first merging the locations with the same proposition, like this. And then we can form the Floyd Hall automaton by adding all these transitions which the Hall triple from its source location to its ending locations holds. This forms the automaton Q1. And likewise, we can form a similar for Floyd Hall automaton for the infeasible trace. So here's the interpolation showing why it's infeasible. And then doing the simple things, we can get Q2 as the result. And then with the principles of the trace abstraction, we can construct V as the complements of the union of these two Floyd Hall automaton here. And notably, the above-mentioned techniques are all standards and in the non-probabilistic trace abstractions and without any modifications. So by the principle, we can then obtain this refined PCFAP that's within refined underlying MDP, where this absence branch becomes going to a place with an observing state here. then this automaton will have the refined structural upper bound as 0.5 as expected, which is the exact upper bound, which is the exact violation probability. So then let us review the core benefits of this structural abstraction refinement methods we just introduced. Then from the introduction, I think one could observe that our method reaches a clear separation between the probability and the semantics. On one hand, the structural abstraction itself does not need to care about the semantics, as every statement has been abstracted as the action labels and as non-deterministic choices by weighing the PCFA as MDP. On the other hand, during the refinement processes, the construction of V does not need to care about the probabilities. Specifically, if we review again the interpolation step, we can see that the probabilistic statements are treated as just skip statements, as they do not affect the logical reasoning of the program. Then we implemented our methods adopting the trace abstraction. As expected, our methods is more robust and generally applicable to a wider types of examples. We collected these examples from a wide range of literatures fairly and tested against some state-of-the-art tools such as Pro2 and Psi. And the experimental result shows that our tool handles 2 times more benchmarks against the state-of-the-art tools with higher efficiency in 73% of the cases. So in the interest of time, in this talk simply present the core idea of this work, and there are a lot more details and more contributions in the full paper. Specifically, to automate the principle, we provide a methodology using the CIGAR framework. So this CIGAR framework can automate the non-probabilistic verification techniques like the trace abstraction techniques. So with this, and we also optimize the trace abstraction techniques to reach the reputational completeness, which means the termination is guaranteed if it really violates the probability, the threshold. And also we will explain more thoroughly in the evaluation through all these, how we select the examples and how we analyze the results, etc. And I think this is all of my talk, and thank you. Yeah, I'm happy to accept any questions.
We've got time for a question. Well, I'll ask you a quick one. So what next? Where are you going next with this?
So hopefully you would like to add some, say, observed structure or something to reach the Bayesian something. Yeah, that's more popular, and we hope to extend it. Yeah, thank you.
Let's thank the speaker. So now we're moving to a different kind of abstraction, not abstract interpretation, but software engineering abstraction. And our speaker is Wenyu Zhao, and he's going to talk to us about work packets, which are a new abstraction for GC software engineering, optimization, and innovation. Thank you, Wenyu.
So thanks everyone for attending the last talk in the conference. So I'm Wenyu, and we are going to talk about a new abstraction to build garbage collection algorithms, the work packet system. And general software engineering wisdom holds that nice abstractions and reusable software often comes with a performance cost. But in our work, we will show you how a new abstraction helped us to have both reusable and modular code while still having great performance. And in other words, you can have your cake and eat it too. Now let's review some of the OpenJDK garbage collectors to put our work in context. So first, G1 is the default garbage collector in OpenJDK. It's tracing and region-based GC. This means that it manages the heap as a set of fixed-sized regions and performs tracing to identify the live objects in each region. It's evacuation only and does stop the water evacuation. This means that to reclaim any fragmented region in the heap, G1 needs to trigger a GC pause, and in the pause, it needs to copy the remaining live objects out of the region before the region can be freed. After that, it resumes application. But the problem here is that doing all the copying in the pause will generally increase the pause time. So subsequent collectors, C4 Shenandoah and ZGC, they all choose to perform concurrent evacuation to reduce its pause time. And from this table, we can see that all the 4 OpenJDK collectors or the JVM collectors, they share many similar algorithm designs. So one would also expect that they can also potentially share a lot of the common code for their common algorithm components. But this is actually not the case. This table is the OpenJDK 21's GC module, and here we count the lines of code for each garbage collector here. And in the green box, only 17% of the code are actually reusable across multiple GCs. All the other parts are just private to each GC. And here we can obviously see that the OpenJDK's GC module has relatively low code reuse and low maintainability. This can also directly affect performance because performance optimization scope can also be limited until we can successfully reuse the optimizations across multiple GCs. And the second problem is about phase-based design. This does not only limit it to OpenJDK. For example, the figure on the right, this shows Emix GC with phases in JAX-RVM. The Emix GC divides the GC pulse into multiple sequentially ordered phases, as shown in the figure here. And the phase cannot start until all the previous ones are all finished. This may sound like it may simplify the design and implementation stage, but this can also lead to low parallelism. For example, this figure is captured by eBPF, and it measures the GC task execution timeline across 23 GC threads. And we can see from this screenshot, there are 3 clearly separated phases. They map to the 3 boxes on the right: reset mark table, scan routes, and transitive closure. So for the last transitive closure phase, it's blocked by both of the previous phases. And even worse, there are multiple long-running tasks in the scan routes phase. They further reduces parallelism and making transitive closure jobs happens even later. So we can see that this phase-based design can sometimes lead to low parallelism. Another observation we had is about GC code locality. So this graph measures the GC code hotness distribution curve for G1, Emix, and LXR. If we pick a point on the Emix curve, 0.05 and 0.99, this means that 5% of the Emix code actually occupies 99% of the GC task execution time. So here we can see that the GC code is actually highly concentrated, and we believe capturing and optimizing this 5% of concentrated code will yield better performance. So based on this observation and the problems, we proposed the work package system as a task execution model that captures, optimizes, and reuses hot kernels. As a result, we deliver better parallelism, better code reuse, and better maintainability. Now let's talk about detailed design. First, I like to emphasize that the work package system is a task execution model, not a GC algorithm. We build it as a fundamental component of MTK, and we support the building of all the 13 diverse types of the GCs in MTK. They include state-of-the-art algorithms like ISO and LXR, as well as many different types of the GC, including Emix, compressor, and other canonical GCs. And both MTK and the work package system are designed in a language-neutral approach. So we support multiple language runtimes, including OpenJDK, Ruby, Julia, and JAX-RVM. So to make our work package system support multiple languages and multiple GCs, we build an abstraction from ground up, starting from the work items and kernels. First, we have work items. We divide the whole GC job into fine-grained work item. And a work item is the smallest unit of GC work. For example, it can be only a heap pointer to trace. The reason we need to have this notion is that we can perform work item stealing. So basically, to make each GC worker be able to only steal one pointer at a time, we can potentially maximize parallelism. And we also have kernels. Kernels are just small functions to process a list of same-typed work items. For example, here is an example of a marking kernel. The work item is a heap object. The kernel is a small function. It accepts a list of objects as input, and it internally has a for loop to iterate over the objects, mark them, and scan their children. So from this example, we can see that the kernels are highly concentrated. They only capture the hot loop, nothing else. This makes the kernel generally has greater locality. And also, the kernels are designed in a generic approach. They don't have any assumptions to the concrete GC algorithm. This makes most of them can be easily reused by most of the GCs in MTK. And also this generic design also making the kernel code easier to optimize, understand, and verify. And finally, we have work packets. A work package bundles a list of same types of work items with their corresponding kernel. And then we schedule and execute those work packets. First, the problem here is that work packets, they can have dependencies. For example, marking requires a properly initialized mark table. This means that marking job cannot start until the reset mark table jobs are all finished. Basically, we represent and encode these dependency constraints as work buckets. So we group the work packets with same dependency requirements as buckets, and then we build a dependency graph over the buckets. For example, this figure shows the dependency graph for the Emacs GC in our system. The dotted boxes are buckets, not faces, and all the arrows here are dependency constraints. Based on this graph, we then perform the dependency-based execution. We first define a set of global algorithm-agnostic GC workers. They blindly push any available work package in any open buckets to execute. And when necessary, they also need to update the work bucket status. So let's take an example. For example, in the graph, for the first work bucket, the stopped mutators bucket, after this one is finished, we can open the next two buckets at the same time so that the packets within the two buckets are available to execute in parallel. And when the reset mark table jobs is finished, we can also open the transitive closure bucket earlier so that we don't really have to wait for everything to finish. And based on this dependency-based execution model, we also build one more layer of optimization, the two-tier work stealing algorithm. And under the common case, we perform work package stealing so that we can steal multiple items at a time to reduce the stealing overhead. And when necessary, we can also make the GC workers be able to only steal one item at a time to maximize load balancing. If we go back to the problem we saw before, this GC task execution timeline across multiple threads, this is what the latest figure looks like. So first, we can see that we successfully merged the execution of most of the packets, especially for the first two phases. And for those long-running packets, they are not blocking the transitive closure jobs anymore because we can now make the transitive closure jobs start relatively earlier right after the reset mark tables are finished. So here we can see that our design optimizes for both software engineering and performance. So now first, let's look at some of the important software engineering benefits. First, our system optimizes for code reuse. We made most of our components reusable across 13 GCs in MTK. For example, we have algorithm-agnostic scheduler. They blindly execute like work packets for all the GCs in MTK. And we have common work packets. They don't have any assumptions to the concrete GC algorithm. They can be directly reused by any of the GC in MTK. 28/49 defined work packets in MTK are such reusable packets. They covers almost all the common steps of a GC, including route scanning, marking, mark table zeroing, sweeping, and stop the mutators. Now with the scheduler and the reusable packets, now defining a new GC is extremely simplified. For most of the simple GC algorithms, the user now only needs to declare their packets and dependencies without caring too much about the implementation detail. However, so far there are some components that are still not reusable yet. For example, complex GCs like ARXA, they may still have special like private packets for their own needs. For example, ARXA still requires like reference counting packets that are not reusable yet. This table shows the lines of code accounting table for ARXA and Emacs in our system. ARXA has relatively more private packets. There are only, there are around 9% of the codes across MTK are dedicated to ARXA, but this ratio for Emacs is much lower, it's only 1%. And this is also the same for the other collectors in MTK. And across the whole MTK, we made 86% of the codes reusable, and this ratio is actually much higher than the number in OpenGDK, which is only 17%. And our system also simplifies the optimization process. I'll give one example here. In another paper we published to OOPSLA this year, we evaluated the ARXA GC in production. And in the paper, we discussed 5 concurrent marking optimizations, including 4 trivial ones and a complex one that completely changed the tracing algorithm from node enqueuing to edge enqueuing. So actually, all these 5 optimizations, they were done in the same concurrent marking work package. And our design of the kernels, they naturally captures this concurrent marking hot loop and make all our subsequent optimization process much easier. And our system also has user-friendly and reusable analysis and verification tool support. I'll give 2 more examples for this one. So first, Huang in 2023 proposed the instrumentation tool powered by eBPF. And this tool was only implemented once on the work package system and is available to all the packets and the GCs in MTK. For example, this figure we saw before, this is generated by this tool. Another example for verification is that Xu in 2022 did model checking on some of the tracing work packets. Because of our design of packets and kernels, they are clearly isolated, so performing model checking on these packets is more easier and also more practical than verifying a whole monolithic implemented GC algorithm. Now let's look at some of our performance benefits of our system. Due to the time, I'll just pick one of the most notable performance numbers here. So first, for evaluation, we implemented the whole work package system in MTK with OpenJDK 11. And here we compare two garbage collectors, Emix, which is a fully stop-the-word GC, LXR, and LXR, which is a reference counting collector with concurrent marking. For both of the collectors, we compare three variants. P stands for a simulation of phase-based design. D means work packets with dependency graph, and S means dependencies with the extra two-tier work stealing algorithm. And we report results across 22 decouple benchmarks. This table shows the GC, the stop-the-word time normalized to the phase variance for both Emix and LXR. We can see that for our D and S variants of our system, we successfully reduced the stop-the-word time over their baseline. And especially for our fully featured system, the S variants here, we reduced the stop-the-word time by 8% for both Emix and LXR. And the second row shows the total time normalized to phases. Because our system at the moment only optimizes for the stop-the-word phases, and both LXR and Emix, they both have relatively shorter pause time, so we did not actually observe a notable change on the total time. For example, on Emix, we only see a 2% of total time reduction. Okay, conclusion. So the conclusion is that we proposed a work package system as a task execution model for building GC algorithms. We have multiple software engineering benefits, including better code reuse, simplified optimization process, and reusable analysis tools. And we also have performance benefits, including 8% of stop-the-word time reduction on Emix and LXR GC. And in the future, we'll continue to generalize the idea to, say, concurrent jobs so that we can also optimize for total time and mutator performance. And we will also continue to add more optimization to the system. Yeah, thank you.
Thank you for a very interesting talk. Do you feel like your nice, regular framework might make GC more amenable to synthesis from generative AI, for instance?
Huh? So it's
yeah, will ChatGPT be generating the next MMTK algorithm?
Oh, well, I never think about that way. So it's, I believe somehow it's possible, right? Well, but I believe I guess for most of the simple algorithms, if you are able to reuse most of the packets without implementing any new things, probably it is possible, yeah. Yeah.
Hello, thank you for the presentation, very nice work.
Thanks.
My question is, okay, if I want this to put it in G1 GC, okay, because in the evacuation phase of the G1 GC, it starts traverse, find the live object. After find the live object, give an address for the new address, then copy this object and continue with the child. How in the context of G1 is going to work? I mean, okay, how these packets are going to work on G1 GC?
Yeah, so basically one of our claims in the paper is that our system is actually general enough to handle most of the GC algorithms. For example, we have total support to the LXR algorithm, right? Basically, LXR does the same thing as what you said that G1 is doing, basically doing the transitive closure, enqueuing objects and scanning out children. And actually, I think in the demonstration, in the pseudocode I gave in these slides, this one is actually much simplified. So basically, in our implementation of our actual marking package, we basically, after in the scan object function, we will scan the object children and enqueue their children. And also, well, this actually one point I did not put in this talk is that work packets can also generate new work packets. In terms of when doing the transitive closure, after you collect a number of children, you can also pack them into new work packets so that other workers will pick them up and process those pointers. So that's how we handle those transitive closure things. And also in terms of the whole generality question, so basically we implemented like multiple implementations of the GC algorithms, as we say that we support 13, and we also have different implementations of, say, the write barriers, and we also have concurrent marking support. We now implemented, I believe we have implemented all the basic building blocks of the G1 GC. But it's just that we haven't implemented the G1 algorithm in MTK yet. But I hope that answers your question. We believe we support all the basic algorithms building it.
Okay, thank you very much.
All right, let's thank Wenyu.
Yeah, thank you.
And thank you all for sticking around to the last session of OOPSLA. I hope you enjoyed it all.